technological breakthrough that propose the synthetic biology. The progress of this cat will contribute to the competitiveness of the bioeconomy. Let's start now with BIOKET Digital Edition. Ladies and gentlemen, good morning. My name is Johan de Koning from IR, the French Bioeconomy Cluster. Welcome to BIOKET Digital Edition. I'd like to thank all the consortium of IBISBA, and in particular, Michael O'Donoghue, for entrusting their workshop to us. Before starting the webinar, few words for our sponsors. They are indeed making a considerable effort, and without them, we would most certainly not be here this morning. I want to pay as well tribute to the whole team of IR who worked hard on BIOKET to make it happen. For those who doesn't know yet IR, I like to play a short movie to illustrate our services.
IAR is the French Bioeconomy Cluster. Let's find out the 7 services we provide you to support your innovations. Tomorrow's solutions are being developed today, from ideas to endorsement and funding of your projects. Our expertise and strategic support will be there to maximize your success. Do you want to diversify your activity to reach a new market? Through our research and consultancy services, we analyze, explain, and help de-risk your business and innovation environment, enabling you to make strategic decisions and identify early adopters and clients. Bioeconomy is a European priority. Having been in Brussels since 2008, we can make sure your voice is heard. We are your ideal partner to access European funding. Innovative startup? Our Investors Club is seeking projects like yours. Thanks to our help, reach out to venture funds and raise the necessary funds to boost your project. Speed up your growth and overcome technological hurdles, thanks to the innovation platforms of our ecosystem. Our Bioeconomy Leaders Network offers you unique business opportunities. Meet your future business partners and develop your expertise at the many events we organize throughout the year. Conferences, business conventions, tech days, so many opportunities to increase your visibility and promote your activities. Grow your business abroad and give your ambitions new horizons thanks to our international missions and delegations. Brazil, USA, Canada, India, Southeast Asia, we will enhance your tech and business partnerships. In a changing world, we will help you adapt your training courses to the needs of bioeconomy. Access tailor-made skills, from the endorsement of your training classes to posting jobs. IAR services are here for you. Find out more on en.iar-pol.com.
2 years ago, we were in Strasbourg, region Grand Est. This year, we were supposed to be in Lille. We thank our main support, the Regional Council of Hauts-de-France, and we hope to be there next year. We have as well some industrial support. The first one are our PLATINIUM sponsors, Genopole in Evry, a leading biotechnology platform in France, quite discreet but very effective. They are active in particular in the health sector, but as well in industrial and plant biotechnologies. And there is where companies like Global Bioenergy, Insect, Abolis, or Innovafit, amongst others, are installed. The second one is the University of Lille, a major university in France with more than 72,000 students, ranking in top 30 of the most innovative EU university. And we like to thank in particular Franck Duménil from the UCCS, a leading authority in the world of catalysis, with in particular his throughput screening platform RealCat, a unique tool in the world of catalysis. We have as well some gold sponsors, amongst which we find our 3 innovation tour. The first one was proposed by the agency of Dunkirk with the visit of the port of Dunkirk, and more specifically, Dodruy van Coenberg, a specialist in vegetable oil recycling, oleochemistry, and biofuels, together with Biotifuel, the total pilot unit producing from lignocellulosic biomass via the Fischer-Tropsch process, biodiesel. The second innovation tour was proposed by Lanolin Stella, a subsidiary of the group De Wavrin, which also includes Isis Pharma and Alpol. This is Falmar and Alpol. Lanolin Stella is one of the world leaders in production of lanolin. They are eager to show us their new molecular distillation unit, which is also at your service for tailor-made production. Pivot, one of the industrialization platform in France for bio-based processes, technologies, and products. They have everything to host the project of your choice and to industrialize them. ValueMag, a BBI project, they were presenting the first webinar of this digital edition. Tournaire, Optimus, Tami Silva, equipment manufacturers at your service for equipment and processes dedicated to green extraction and purification. P&O, a leading consulting company for your R&D project. Accents, French technology transfer company, which markets many processors to transform biomass. They have an impressive portfolio of technologies. Last but not least, ERD, no need to present them. They are so much known in the field of process scaling up, and in particular with their 220 cubic meter fermenter and the size which allows them to make industrial production to order. Their industrial culture and experience in both biotechnology and green chemistry makes them a first partner to industrialize your process. We have as well some silver sponsors, Erodia and Novaset, specialists in purification, Noveal, the new name of the industrial subsidiary of L'Oréal, and Vito, a Flemish research organization in the area of clean tech, sustainable development, known for the H2020 Biohorizon project and its LignoValue pilots. Finally, we'd like to thank all our bronze sponsors, and in particular, the subject of our webinar today, IBISBA. I won't mention them all because for fear of forgetting one, but you can discover them in this slide, and they are as well all in our website. It is now time to switch to the program. We do hope you have appreciated the first two webinars, and we hope that for those who participate to the virtual B2B, you could identify new opportunities of partnerships and businesses. The webinar is now closed, then no way to see, let's say, this slide, sorry, if I've forgotten to remove it. In a few minutes, we will start with the IBISBA and its webinar on biofoundries and bioprocesses. It will be an immersion in the heart of synthetic biology with European and worldwide best actors in the field. Before, we are happy to make some announcements. Few coming interesting events for the bioeconomy. Next week, we organize in the scope of our Intercluster 3BI a free live webinar dedicated to post-COVID opportunity for the bioeconomy. We have 3 invited speakers, one from Vereniging Nederlandse Petroleum Industry, one from Neste, and one from SABIC. I'm sure it will be a good opportunity to go deeper in the bioeconomy opportunities during this crisis. In September, BIOKET Digital is back with another Horizon 2020 project, the project Enabling BPP, a project encouraging the creation of efficient and structured biomass supply chain for the production of bio-based products. Not to forget as well, dates of event for this fall. They are all digital. I'm talking about the World Bioeconomy Forum on September 10 and EFIB on October 5 and 6. Finally, 2021 hopefully will be a better year than 2020. And please, we like you to save the date for the other event we organized together with ACDV and InfoPro. The Plant-Based Summit is back, and it will be in Reims next June. PBS, as we call it, is a congress dedicated to bio-based solutions. To bio-based solutions. We have a brand new advisory board this year, and an original and much more international program is under construction. We invite you all to submit your abstract. The call for paper, it's already open. But please, if you should just select one event for 2021, don't forget the most important one, the one which is the subject of today on a digital edition. We hope you're not going to miss it. BioKet, our on-site event, will be in Lille next March 2021, and I want to see you all next year. Now it's time to start the webinar. We are happy to welcome Nick, and all the speakers on the floor for this webinar. Good morning, Nick. Good afternoon for those who are in Europe. Welcome to BIOKET Digital. Happy to finally being able to organize this webinar for you. The antenna is yours. I'll stop sharing my screen. The floor is yours.
Thank you very much for that introduction. I'll put on my screen. Okay, so you should all have the my few introductory slides on the screen at the moment, and this is just briefly to introduce the logic of the session. Let me put it on the full problem. Yeah, so this is basically just the title of the of our workshop today. It's going to be split in two halves. We're going to have some invited speakers to give you some baseline information, and then we're going to open it up to a round table. So that should be, hopefully, should answer a lot of the questions you might have on the Biofoundry logic and how that fits into the biotechnology scenario. Just to put you into the picture a little bit more, the logic behind this workshop was to sort of bring everyone up to date on where we are on the Biofoundry technology. This is changing the way we do a lot of our biotechnology today. The extent to which this is a rupture technology, I'm hoping we'll get good ideas for that. We have a couple of speakers specifically on the Biofoundry. We're also wanting to introduce you to IBISBA. I'm not going into details what IBISBA has because Mike, who is running the IBISBA show, will give a talk on that along with Major and others. But basically the question is going to be today, how do we interface this Biofoundry technology, which really gives us extraordinary high throughput strain engineering possibilities, to the other aspects of the bioprocess engineering, so we can create, as you can see at the bottom of this slide, an accelerated industrial biotechnology pipeline, being able to exploit synthetic biology, but to bring it to market very quickly, much quicker than we're able to do at the moment. This is the underwriting principle behind IBISBA, and I think we should get some pretty good information about what is possible, what might still be a little bit difficult, and where our dreams should be moving us forward in the next few years. So just quickly then, the basic of our program today. We got an introductory talk for half an hour from Paul from Imperial College. I'll give you a brief introduction of each of them. We'll then move over to the IBISBA side, the way we deal with it, an introduction from Michael. And then from we move over to how we actually manage and integrate the actual operations, how do we treat the data, and then move over to a practical application. Once you've got these strains, how do you scale them? How do we take that potential through into real manufacturing processes? And we'll end that first part of the conference with a very industrial view from Sunil, who is not online at the moment because it's still about 5 o'clock in the morning in San Francisco. So he'll be actually joining us just before his talk. We'll then have a quick bio break, perhaps, if we're not running overhand, and then move over to the round table, which Michael will chair. Since this is not quite so interactive as a physical workshop, you will be asked, if you want to ask questions, then please register on the Q&A button in your Zoom toolbar at the bottom of the page. And if time permits, we'll try and get some of these questions answered. I've been informed by the organizers that if you actually put your name, they will actually register the question. If we don't have time to finish it, to answer the question, we'll probably be able to put you in touch with the speaker so they can sort of get some dialogue going beyond that. So that, for me, is the introduction, while I'm just closing down my screen and handing over to Paul. Put this back on. Okay. So my screen stopped. So Paul, you can begin loading up your on your presentation, I think now, and I can use that time while it's coming up on the screen to give you a brief introduction to Paul. He is, of course, installed now for quite a few years at Imperial College in London. He set up, along with Dick Kidney, I think, the Center for Synthetic Biology, and also a national UK innovation. And that's things which date back to about 2013, one of the initial synthetic biology centers in the UK. Slightly later, in 2016, he set up the Biofoundry. And even more recently, only a couple of years ago, he actually got involved in setting up the Global Biofoundry Alliance, which regroups different biofoundries from around the world. So if all is okay, Paul, we can hand it over to you. You should have the screen possibility to share your screen.
Thank you very much, Nick and Michael, for inviting me to talk today. Please let me know if that's worked okay.
Yeah, it's up on the screen.
Great. So thank you very much. I just want to give you a kind of, I want to start my talk by just a few little reminders. This is an interesting quote from the United Nations Development Program. By 2030, we'll need to increase food by 35%, water by 40%, energy by 50%, and we're going to need innovative solutions to meet this demand while conserving critical natural ecosystems as a necessity. And so the question, I think everyone in this whole field of biotechnology is, how do we move to more sustainable processes and generate new types of economy for a world in 2050 with the global warming, climate change, and resource limitations, and what technologies can we harness? So this idea of transitioning from a petrochemical-based kind of economy to a more sustainable bio-based bioeconomy is one of the great drivers, I think, for biotechnology at the moment. And I think it's a really exciting era for us to be in. So I think that's happening. If you could turn off my screen, Nick, that would be good, because I have an unstable connection. I'll stop my video. Right, there we are. I think it's a very exciting area, and I think we're at the start of a really new biotechnology revolution. And I think some of the new tools and technologies of synthetic biology and engineering biology are driving this revolution. So I think, as I just said, I think this technology is part of the revolution, and I think biofoundries are a key part of this, and I'll tell you why. So the question is, what are biofoundries? Why are they a new concept? So as you know, synthetic biology sort of considers developing tools and processes to manipulate biological systems at the genetic level, obviously for a variety of different applications. It clearly biotechnology, but it's biotechnology with a kind of different way of doing biotechnology, if you like. And the reasons that it's happened, I think, is there's been a convergence of different things. There's the technologies of molecular biology have become so mature and very, very powerful. We have this wonderful convergence of disciplines between the life sciences, computing, engineering, physics, and this cross interdisciplinarity is a very common part of modern research. And then, of course, the costs of reading and writing DNA have come down considerably, and particularly writing DNA, which is becoming now at a cost that allows people to think about large synthetic pieces of DNA to purchase, rather than having to do all the molecular biology cloning techniques that we're used to. At the core of synthetic biology sits this design cycle. And this is a very simple thing. It's sort of engineering kind of thinking, if you like, into synthetic biology. And this is where you can design, build, test, and learn kind of cycle. And the designing would be computational. The building would be physical assembly of genetic elements. The testing would be to see how those genetic circuits, plasmids, pathways, whatever application you're trying to do work. And then the learning would be to analyze all of that biological data and see if we can develop intuitive design rules for biological systems. And I think this is at the core of what people are trying to do in synthetic biology. And this idea of computer-aided biology, this is a nice slide from Synthase, which is a UK startup. And I think this is the idea of simulation, design, being at the core of thinking about biology and biological applications. and then resulting in those designs being interfaced into the experimental execution of those designs to provide data which allows you to go around this design, build, test, learn cycle. So I think this idea of biotechnology becoming essentially computer aided is a key part of one of the drivers. So in design, there are many different software tools available, particularly in the academic developments and also in the professional world as well. And this is continuing to expand. There are standard languages, synthetic biology open language. This is just a very small example of some of the tools that are available now. And the build, I mean, this is our own Foundry, and this is just a protocol that we developed where we can build up to 1,000 different plasmid constructs a day, and we can do 384 transforms a day in a fully sort of automated way. In the tests, of course, you have all the range of omics technologies, all the different types of analytical techniques that we commonly use in biology, from mass spectrometry to microarray and RNA sequencing for transcriptomics and for proteomics, for MALDI, and all these kind of methodologies can now be applied to analyzing the outputs of your genetic designs in that test part of the cycle. And then in the learn, we have many different approaches. This is just straightforward, well, not straightforward, but this is a well-used design of experimental framework, which is used to explore experimental space, which we use a lot in the Foundry context. And then, of course, there is the new developments of machine learning and data-driven learning, which are becoming online. And there's some really interesting challenges about how we can bring this omics data together into a machine learning environment so that we can start thinking about design rules for biological systems. So Biofoundries essentially facilitate this design, build, test, learn cycle to accelerate the prototyping of biodesigns for specific applications. That's essentially what they do. And so the idea of prototyping has been around in industry for a long time, but surprisingly in biotechnology, the prototyping environment has been a little bit unclear. And I think what synthetic biology provides is a very clear prototyping environment around this design, build, test, learn cycle, which allows researchers and biotechnologists to think systematically about their designs of strains for bioproduction or their biosensor strains or even new biomaterial production. And I think this prototyping environment, a lot of it will be carried out essentially in the Biofoundry. So essentially, I would argue that the Biofoundries are acting as the kind of the wind tunnels for airplane designs, but they're the kind of the wind tunnels for biotechnology. And so what are they? So they're integrated infrastructure for prototyping genetic designs in this multi-user environment. So liquid handling robots, integrated analytic tools, automation of molecular biology protocols, the high throughput assembly of large-scale DNA, synthetic DNA fragments, constructs, genome to genome scale, high throughput testing of those genetic constructs in cells, and then of course built around a software environment that contains laboratory information management systems, the BIOKET design rules for when you're building new biological systems, and of course the design of experiment approach to experimental space that I described. And then the application of AI and machine learning is now really featuring a lot in some of the developments. And of course, access via the cloud is also a very interesting feature. Now, Biofoundry developments, interestingly, happened early in the synthetic biology startup. So here is Amaris, Ginkgo, Transcriptic, and Zymergen. And as you can see, a lot of these companies built their business models and their capabilities around the Biofoundry concept workflows. But it's only more recently in academia that Biofoundries have really begun to take off. This is our Biofoundry, the London Biofoundry. We provide this industry academic interface with a suite of instruments and workflows. This is our team, and we obviously have a large number of companies we work with and a large number of researchers we work with. And in our Biofoundry, and I think this is common amongst many different Biofoundries, we have a kind of what we call a full synthetic biology stack, where we've got automated liquid handling systems, we've got measurement systems, analytical systems, we've got software tools, analytics. We're also looking at cell-free workflows, strain engineering workflows, and DNA assembly workflows. And this idea of design, build, test, learn, I put another bit on here, which is the report. And I think what we do is that we end up developing new workflows. We end up thinking about new proteins, new biomaterials, new compounds, new genetic tools, new production strains, working with companies. But we also work with instrument companies and also software companies. So for example, we've been working very closely with Analytical on some of their workflows. and Agilent as well, and Riffin in terms of some software tools. And also, as part of the Biofoundry, it sits within the City, which is an innovation and knowledge center, public-funded innovation and knowledge center, which aims to try and translate and accelerate academic and accelerate industrial R&D, and through the Biofoundry. And on the right there is a whole bunch of companies that we've worked with, and we've got a whole lot more actually that I couldn't fit on this slide, but that's just an example of some of the companies that we've helped in terms of their technology developments. So some of the workflow developments, I described that one, that's our DNA assembly workflow. This is a rapid prototyping workflow for yeast pathway engineering. This was work with Tom Ellis that we published recently, where we could do a completely automated construction and testing of 88 yeast expression plasmids built on BIOKET design rules. This is a cell-free license. This is from my own group, where we've got a rapid and automated prototyping platform for cell-free systems. And then as a startup project, this is a nice project with an Imperial College startup called AmbiMass. And this is a project around REIMS. And this idea of direct analysis of growth colonies within a plate by mass spectrometry to analyze products is a very interesting development. And this is with Zoltan Takets, who is one of the founders of this type of technology, this type of mass spectrometry technology. And on the left there, you can see that you can get some very rapid high throughput measurements using the AmbiMass, or they call it AmbiScreen, which is in blue there, which is essentially ionizing colonies grown on a plate to look for products or to look for particular metabolites. And that company is now founded and is working closely with us in the Foundry. Now, because we've been through, or we are in the middle of this COVID world, one of the interesting things I want to highlight, if that's okay, is to show how Biofoundries can have a role in not only underpinning a lot of the prototyping for biotechnology developments, but also can be pivoted into national emergencies. So in the UK, we've been really that we needed more testing. And so what we did at the Biofoundry was to identify a workflow that we could pivot our Biofoundry in to develop high throughput COVID testing. So we started in early February. And this is people in my group that led this project. And we validated our workflow using synthetic viral-like particles in our lab. So it means we could work in category 1 facility. We did a rapid implementation and validation in St. Mary's Hospital and Charing Cross, and both platforms now we actually transferred over into those hospitals, into those pathology labs, and they're actually carrying out COVID testing, and each platform can carry out around 1,000 tests a day. The interesting part of that process was the ability to adapt our infrastructure and to also quickly develop workflows. Now, we made our workflow fit into the existing COVID testing workflow. We didn't have time for new technologies, new work, because we had to get it UCAS or accredited as an accredited clinical diagnostic testing workflow. And so we dropped in a workflow into the existing qPCR methodology. But we did that very quickly and effectively. And because of our adaptability and flexibility, we were able to develop reagent agnostic platforms, which got around some of the problems that were existing in the world with reagent supply chain issues. And so this is just an example of the workflow. And this is a QTAR 96. The beauty of the workflow is that it occupies very little space. And of course, this 2-Felix platform, we're doing up to 1,300 samples in a 12-hour period. It only occupies a very small part of the laboratory and a small number of people use. So it's very interesting. And actually, since our developments, what's happened is that the Northwest London Pathology, which is the pathology lab for Charing Cross, have now purchased 4 platforms, which they're now doing all of their COVID testing on. This is the synthetic viral-like particles as an internal standard. I won't go into too much detail about this, but it's particles and put the RNA of the SARS-CoV-2 virus in there as an internal standard when you're developing your workflow, which is RNA extraction and RT-PCR. And this is the Felix workflow for RNA extraction, speeded up enormously. But we turned out this Felix workflow was incredibly reproducible, and it allowed, we analyzed a number of different kits. And we were getting very, very good sensitivity using our viral-like particles. both for RT-PCR, which is on the left here, and also for different primers. And this is all using our synthetic viral-like particles. And then for different kits, this is the Promega and Antigen, and we've now done 4 different kits, and we've validated all on the platform. I won't go through all these details, but again, you can do multiple PCR kits. So the idea of getting away from reagent dependency was a key part of this. And now this is the platform sitting in Charing Cross Hospital, and that's the validation data, and it's now undergoing UCAS accreditation. Working with pathology labs has been a very interesting time because they're incredibly strict on their quality control and quality assurance, and I think that's been really very helpful. Of course, we, like biotechnologists, we're interested in new technologies. So this is now a CRISPR and LAMP workflow that we developed for COVID-19. And this is again on our synthetic viral-like particles in our lab. But then we translated that over into the clinical labs. And this is some patient data now showing exemplar patient data. On the bottom left, there is a CRISPR assay against COVID-19 showing different CT values, different levels of viral abundance. And on the right, there is a LAMP assay, which is a simple colorimetric pH change assay, again showing different viral loadings and getting quite nice data for patient samples. Finally, I want to describe, I'm not sure how much time I've got left, Nick, but I hope I've got time. I want to describe the Global Biofoundry Alliance. The reason I want to describe this is a relatively new organization, and it's a very exciting organization, which I happen to have the honor of chairing at the moment. So as I said to you, public funded biofoundries are being established worldwide. And this is a very interesting, relatively new phenomenon since industry have startup companies in SynBio had already thought about this biofoundry concept. And this integrated infrastructure for testing and prototyping biotechnology research has really taken off around the world. And so there are many public funded biofoundries being built, and we just decided we'd get together and establish this Biofoundry Alliance to coordinate activities across the world. This is the first meeting in London where everyone just paid their way to come and have a chat. Is this a good idea? Is it a bad idea? And then we finally thought it was a good idea, and we launched the Global Biofoundry Alliance in Japan last year in May 2019. And what was interesting about the Global Bio, we now have 29 members distributed around the world. This is the latest membership list. And you'll see that we have biofoundries in China, Asia, Europe, and the North American continent. Part of the Global Biofoundry Alliance is to develop, promote, support non-commercial biofoundry establishment, to collaborate, communicate, to develop responses to technological, operational, and other types of common challenges. The COVID challenge has been a very interesting test case on that. And also to enhance the visibility of non-commercial biofoundries and explore globally relevant projects and impactful grand challenge projects. We signed a memorandum of understanding, which is obviously not a legal binding document, but it was a spirit of cooperation which allowed everyone to work together, and everyone has to sign this. In that memorandum of understanding, we're all committed to sharing pre-competitive knowledge know-how. We're committed to collaborating, developing common protocol standards, software, and interoperability. We've got some working groups established. We're also working individually and together to engage different policymakers and other types of stakeholders. We really want to promote the importance of automation, and we also want to organize our conference website and communication tools. So these are the current working groups: metrology, reproducing data quality, software, business models, sustainability, outreach, industry, and grand challenge and demonstration projects. Sort of the pre-competitive activities that we can tackle are some of these things listed here. So for example, techno-economic lifecycle analysis models, metabolic pathway engineering design tools, obviously BioCAD and computer-aided tools, workflows particularly that are relevant, industrially relevant microbial hosts and onboarding. So bringing some of these industrially relevant hosts into the biofoundries and looking at how we can develop genetic regulatory elements or characterize those new microbial strains. Proteomics, metabolomics methods and analysis, and of course some of the modeling and the machine learning approaches, informatics infrastructure, and essentially trying to work on different mechanisms. So using this freely open source idea for academic use and for academic commercial licensing. So there's different models of how we can work. There's a lot of co-development opportunities within the GBA. Again, new hosts, metabolomic methods, informatics methods. One of the key things that I'm really interested in is Biofoundry performance metrics. So how do we actually against each other, and what would a performance metric look like for a Biofoundry? Would it be this unit operation capacity? Would it be data generation, bioprocess commercialization? What would be those kind of metrics? And we're very interested in exploring those. So the metrology group at the moment is canvassing all of the metrology infrastructure at all the publicly disclosed Biofoundries, and that's been a really interesting exercise, identifying some of the freely open source metrology methodologies, and prioritizing developments for open source measurements and protocols and reference materials. In terms of non-GBA members, how do they engage? So non-GBA contributors can engage, but they have no decision-making authority, no influence on the prioritization, but they can be informed of what the software group is working on. For example, the software group have really grabbed this quite a lot, and they can contribute to freely open software projects. And I'd like to thank Nathan, Matthew, and Natalie, who are my co-chairs for the GBA. So in summary, I'm sorry that's been a whiz through Biofoundries, but they provide this adaptable infrastructure to accelerate the DBTL cycle for prototyping genetic designs for specific biotechnology applications. The Biofoundries can be pivoted into new national challenges and emergencies, and the COVID testing work we did and others have done around the world has been really interesting to point this amazing infrastructure sitting there that can be readapted into crises like COVID. They're both academia and industry facing. That's what's really interesting about this infrastructure. It can work with academia, it can work with industry, can promote startups, can help new technologies be developed in this prototyping environment. And the GBA is a very large growing alliance of non-commercial biofoundries, which again aims to promote sharing and open source technologies worldwide. So finally, I'd just like to thank my team, in particular, Michael, Miles, Marta, and Marco, who were amazing in developing the COVID-19 testing platform, which was done over a period of 7 weeks, and they worked day and night to get that validated to the level that it could go into a hospital. And this is some of the members of my lab and also of the Biofoundry, and I thank you very much for your attention.
Okay, thanks a lot, Paul. I'm amazed so many slides in such a short time. It's great. I'm not sure if the audience is thinking about putting their questions into the Q&A, but while they're doing this, I got one question I'd like to ask. It's, Biofoundries generate a huge amount of data, and we don't always exploit that data to the utmost. Just wondering if the move towards artificial intelligence, will it actually get us to a point where we can think about getting to the same result quicker because we're gradually building up our knowledge base? I don't know if you have any thoughts about how that is likely to be implemented.
Yeah, no, absolutely, Nick. I mean, you're spot on. I think one of the great challenges I think we all face is the learn. Okay, if you follow the design, build, test, learn cycle, which is what Biofoundry, if it's a learn side, so the learning. What data do you need to learn on, and how do you learn, and how does that learning implement the whole process? And to be honest, getting around that cycle, when we talk about the design, build, test, learn cycle, it's actually quite a complicated cycle to get around several times. So one of the big challenges is, how do we integrate multi-scalar data? What level of data do we need to make decisions that would allow improvement in productivity or yields, which I guess would be the target function for a biotechnology project? And how does that data, and I guess it's through doing multiple experiments, multiple data captures, and multiple learning approaches that we're going to build up that experience. But I think the experience is limited at the moment, but it's a very, very important point. And ultimately, I would like to think that we would have a set of design rules that would allow us to circumnavigate some of the exploratory work we have to do at an initial biotechnology strain, development.
Okay, I got one question coming through the forum about how easy it is to use filamentous fungi in the Biofoundry type of approach.
That's a very good question. I haven't. It's certainly. I'm not aware of that chassis being used yet, but I don't know every chassis that's been worked on with all the Biofoundries. That's a very interesting chassis. I know that there's a very large onboarding project going on in the Agile Biofoundry in the United States, led by Nathan Hilson. And I know that filamentous fungi and some of the other kinds of organisms are being looked at, but I can't actually tell you on the progress of that. But it's a very interesting question. Another challenging part of Biofoundries, of course, is mammalian cells. Also, organisms like actinomycetes and other kind of strange organisms that have, have morphological features to growth are quite complicated, I agree. But I think they're very well worth exploring and onboarding into Foundries.
Okay, more coming in, probably have one. Okay, it's just a thank you for the answer. So yeah, I think thank you there then for Paul. We're looking one eye on the clock. We'll move on.
Absolutely.
And we'll talk a little bit later on the round table, certainly, it's, to sort of open up the discussion. Yep. So we're going to hand over, Mike, you can be setting up your screen. We're going to hand over now to Michael O'Donoghue, who got his PhD back in the UK in the early 1990s, and then moved over to France, as so did I a few years earlier. Has been working within the Agronomic Research Institute for quite some time now, since 1996, developed his own team on protein engineering, and is now heading up a whole division of INRA, the transformative division. More specifically in the context, I think, of this particular workshop, Mike was really the leading light, pushing us all in to think about how we should set up a European network to accelerate the transition from synthetic biology through into manufacturing. So he's the ideal person to give us a quick talk, an introduction to what is behind the IBISBA network. Mike, the floor is for you.
Okay, thanks, Nick. So good afternoon to everybody, and good morning for those who are not in the European time zone. So as Nick just said, my job this afternoon is just to give a brief introduction to IBISBA, and then you'll have more details from my colleagues, Maria Pentila and Katja Paszczak from Fraunhofer. So first of all, IBISBA, what is it all about? IBISBA is a European infrastructure, research infrastructure. It's actually a distributed European infrastructure that aims to support the transition to the circular bioeconomy. So we've just heard how Biofoundries and the bioeconomy are linked together through Paul's talk. And what we aim to do with IBISBA is to improve the ability of industrial biotechnology to respond to market demands for sustainable products. So IBISBA as a European infrastructure has been on the European Strategic Roadmap for Research Infrastructure, the S3 roadmap, since 2018. So it's a newcomer to the roadmap. And so now we have, since 2018, we've been given our I guess, a 10-year mandate to get this thing up and running. So the purpose of IBISBA is, as I said, to enable the circular bioeconomy by accelerating bioprocess development. And so this is very much linked to the things that you've just heard from Paul. Why the bioeconomy? Because the bioeconomy requires new technology. As you know, the success of the petroeconomy is very much linked to the success of chemistry and the development of chemistry over the 19th and 20th centuries. The chemistry sector really heavily supported the success of the petroeconomy. And in a way, the bioeconomy also needs its technology. Of course, chemistry will be a part of the equation, but the other part of the bioeconomy equation will be biotechnology. And this has been recognized for quite some time. As you can see here, you can see an OECD report that was published in 2009, and they considered in this report that a bioeconomy is a world where biotechnology contributes to a significant share of economic output. So with regards to biotechnology in Europe, it's very interesting to note that Europe is really, I would say, the traditional leader in industrial biotechnology. It was where industrial biotechnology really emerged in its modern form. And in Europe, we're still can actually identify quite a lot of strengths of the European industrial biotechnology sector, even if these days industrial biotechnology is no longer a sort of a monopoly for Europe. Of course, this area has now budded and flourished in many parts of the world. However, just on a McKinsey report that was published last year in August, focused on where are the strengths in industrial biotechnology in Europe. And one of the major conclusions of the report is biotech is still a very strong area in Europe, and is also a strong foundation for new growth and new innovation in Europe. And the interesting points that you can take home, messages that you can get from this report, is that there is a lot of interesting biotech hotspots in Europe, but they're very fragmented across the European continent. We have world-class science in Europe to support industrial biotechnology, and we also have some of the top biotech innovators and a lot of talent in Europe. However, of course, there's always room for improvement, whether we're talking about European science or science as a whole. And what we know from other reports that have been published recently, and notably a EuropaBio report, EuropaBio being the European Organization for Biotechnology in Europe. What the report tells us is that industrial biotechnology delivers a wide range of manufactured goods for a wide range of sectors, from chemicals, fuels, food, well-being, materials, the pharmaceutical industry. And as you heard earlier, how in times of emergency that some biofoundries can be used to develop clinical diagnostics. So you can see the wide range of areas that biotechnology can be used to. And biotechnology actually figures among Europe's strengths in terms of revenue. So it represents 31 billion euros in 2017. So you could imagine that maybe it represents a little bit more now. However, 31 billion euros is a lot of money, but actually it's comparatively speaking rather small when you compare it to the chemical industry, which actually represents 4 trillion euros worldwide. So you can see there's still quite a big gap between the development and penetration of industrial biotechnology in the manufacturing world compared with the chemical industry. So what are the challenges for industrial biotechnology? Well, industrial biotechnology in the new emerging bioeconomy will need to deliver cost competitive, flexible and efficient manufacturing processes. As we've just seen, only about 3% of projects at the current time are actually bio-based, and bulk chemicals are still extremely difficult to make through bio-based routes if you want to aim for economic viability. However, new knowledge and breakthroughs in biology are significantly changing the playing field. And again, we've just seen that through Paul's talk. Biotechnology still encounters quite a lot of difficulties when it's put into head-on competition with the petrochemical industry. And again, we've just seen that synthetic biology is offering some quite exciting prospects for future bioprocess development. So what needs fixing, or maybe I should say, what do we in IBISBA think needs fixing? Well, the first thing that needs fixing in the industrial biotechnology area, and when I say fixing, I mean what needs improvement. We need to make greater efforts to draw biology and chemical engineering together. Of course, industrial biotechnology is very much supported by the biological sciences, and we can see, for instance, the work that's been done in London in the Biofoundry, that it's very much life sciences and biologists that are pushing this forward. And we know that the key to industrialization goes through chemical engineering, and at least in academic circles, these two disciplines are still quite far apart. They operate in different worlds, and so we need to be able to create bridges across these communities, and probably go towards the creation of a domain-specific knowledge commons that can be used to share knowledge between the communities. We also need to diminish stop-start project life cycles. We have some very interesting work going on at any given time in our laboratories, but often this is linked to projects, and these stop. Sometimes it involves collaborations between European laboratories, and once the funding runs out, things stop again. And then it's very hard to restart these things afterwards. The other thing that's very difficult to reconcile with modern thinking, notably when you think about research spending, is research duplication. Of course, testing the robustness of research results is very important. But when I talk about research duplication, I'm talking about pointless research duplication, which mainly arises due to the fact that we don't actually know that it's already been done elsewhere. We think that this can be facilitated by using modern data science, improving the fairization of project information so that people know what exists and what's been done. And of course, all this is going to be accelerated through the use of cloud technology. We also think that to improve industrial biotechnology, and this is linked to the first point, we really need to improve success at scale-up. So when things move out of the laboratory environment and move into the pilot scale and demonstration scales, to make industrial biotechnology into a serious competitor for other industrial technologies, this really needs to be improved. So we need to develop new approaches and tools to design and construct robust processes right from the outset, from the very early stages. So where does IBISBA come into this, and what do we think we will be able to do with to solve some of the problems and help industrial biotechnology to reach full maturity? Well, IBISBA, for a start, means Industrial Biotechnology Innovation and Synthetic Biology Accelerator. So you can see that we're sort of embracing both synthetic biology progress, but also in the wider scope of industrial biotechnology and bioprocess innovation. So IBISBA is a world-class, knowledge-rich European industrial biotechnology infrastructure. As I said, it's a distributed infrastructure. So our facilities are spread over 9 countries, 9 European member state countries, and in 18 different research institutions at the present time. We've developed a single broker access to a catalogue of best-in-class infrastructure. So this catalogue now exists, so you can consult it on the website, and you can get access to different infrastructure in different countries just by going through our single catalogue. It's a network of facilities which we are trying to link up through cloud technology and using cutting-edge data science, and we actually have a data and project asset hub that already exists, and you can actually go and visit that and eventually apply to get access to the hub. We have a program of subsidized transnational access. So at the moment we have European funding that allows us to launch project calls, so people can actually apply to get access to our infrastructure. Access is generally fully subsidized, so 100% subsidized, but it can be less depending on the nature of the request. We have partners dedicated, all our partners are dedicated to reducing research duplication and wastage of resources. So we're trying to actually harmonize our strategies and think how we can actually streamline investments in our different member states, so that we continually offer the best that we can across Europe. We have an ambition, which is a long-term ambition that we're working on, to operate seamless end-to-end research development and innovation pipelines. So the idea is that we diminish, as I said, the stop-start effect of project-based research. Finally, I think this is really important, and Paul said earlier that the Biofoundries are actually quite nice interfaces between academia and industry, and IBISBA is very clearly open for business with all stakeholders, so working with public researchers, but also with companies, and even the transnational access program is accessible by companies, and we've actually already had some successful projects with SMEs. So our vision for tomorrow is to create a world-class, knowledge-rich European industrial biotechnology hub that will operate a research infrastructure network driven by cloud technology and cutting-edge data science. As I said, it's not a dream. We want to be able to provide single broker access to best-in-class infrastructure to public and private research and development players. We want to be able to facilitate access to research infrastructure right across Europe and to all European researchers and also beyond. Promote sharing of knowledge assets among the IBISBA research operators and with users. Create the conditions for seamless end-to-end research and development pipelines, and work with public and private stakeholders to add value and optimize the use of resources. And so with that, I would like to thank you for joining us this afternoon. I hope you'll enjoy the rest of the afternoon with us. And just to mention that you're all invited to get into contact with us, of course. And if you would like to join our stakeholder community and get more information, don't hesitate to send us a mail. So with that, I'll hand back over to Nick.
Yeah, thanks, Mike, for that. I got a question which really rejoins one that I had anyway. Basically is, the question is, how do you define best in class? And I think that's the question from the audience. And my correlated question would be, how open would this network be to include some of the emerging future best in class so we can move it and fill the gaps? Huh?
Yeah, so first of all, best in class is, I think we already have some of the leading research institutes in the biotechnology area in Europe in the IBISBA network, but we don't, of course, have all. We're not an exhaustive network, but we're an open network. And so at the moment, as you can see, we have 9 institutions from 9 member states, but we're not a sort of a closed club. So we're always on the lookout for a new infrastructure that can actually provide complementary services to those that we already offer. And we're actually performing in the framework of a project that we're running at the moment. We're performing a science and technology gap analysis to actually appraise the situation and see what we need to build our capacity in the future. So it's a two-way process in a way. We're quite open for people to get in contact with us and to tell us about their infrastructure and how they can actually join in our efforts. And we will also be going out to actually find and identify the right infrastructure in the future.
Okay, thanks then for that, Mike. And I think, yeah, in the interest of time, we are running slightly behind time, but pretty good. We'll hand it over to the next talk to Mary, who can load up a screen, I think, at the moment. And then while she's doing that, I can give you a brief introduction so you know who's going to be talking. Professor Pentilla then is really quite experienced in the field of industrial biotechnology and moved into synthetic biology at one point down the line. So she's running at the moment part of this aspect within VTT, Finland's, I would say, major biotechnology center. A lot of experience in metabolic engineering, protein production, some plant biotechnology, etc., etc. The list is quite long, as you'd expect from an institute with more than 90 people working there. She's also one of the founding members of the IBISBA platform, and I think today she's going to talk to us, effectively, I see the screen now, on knowledge management and the way that fits into the IBISBA Biofoundry operations. Maya, the floor is yours. Huh?
Okay, thank you. I hope you can see my slide
on the screen, yeah.
And see the cursor. So I'm happy to try to sort of concretize a bit how in IBISBA we are building the Biofoundry operations and really overcoming the one could say the challenge also of integrating the different institutes which are partners of IBISBA. And at least for me, the sort of one of the key aspects is that we would need to build a common mindset as a service provider, whether the service is then a research type of collaboration with academic partners, or whether it's a service type of projects, for instance, with companies. And how then we can ensure that when doing this, so that we can use the best science and technology capabilities of the partners for cutting edge approaches. This may mean that we have, or means that, that we have harmonized operations to do some of the workflows, and also many maybe harmonized protocols so that we can ensure that we have high quality service. And this way then we also accumulate unique IBISBA know-how on the operational excellence, and of course the bioengineering excellence, and we need to then pay attention also high quality data generation, management of the data, and utilization of the data. So IBISBA strengths lie in the capabilities of the partners, and these are rather broad. So we have excellent infrastructures, from high throughput robotics, screening platforms, automated bioreactors, to pilot scale operations. So the TR levels range from 2 to 6, let's say. Obviously, the partner institutes have very advanced different types of analytics, and then we have data management tools and strategies. And their science and technology capabilities of the partners are really covering very well, with long history of the relevant sort of fields in biotechnology, which are enzyme engineering, protein production, metabolic engineering, synthetic biology tool development, and various different organisms. Yeast, filamentous fungi are included in the platforms, bacteria and algae, and importantly, not only the model organisms, but also of strains and species of industrial interest. Capabilities range from biochemical thermodynamics to production physiology, and then different kinds of computational tools, from enzyme modeling, cell modeling, to process level modeling and analytics. What is also, and Mike sort of emphasized that Europe is strong in industrial biotechnology, and also the partners we have in the network have had many industrial collaborations, and in particular also have a keen interest in bioeconomy and circular economy. So if we go beyond the biotechnology or synthetic biology per se, so the institutes of course have vast knowledge in different raw materials, the processing on one hand, and then downstream product purification and chemical processes. Various recycling concepts have been carried out, and environment aspects considered. And then what is also important, that partners have knowledge on research to market cases in production of fuels, bioplastics, and pharma, through in particular the collaborations with industries. So we have then in a way a possibility with the EU funding to really look how we can create the IBISBA platform so that it would be high quality, seamless, more and more automated, but also flexible because the clients may be different. So how would we build a platform? And there are basically two different types of actions where we focus on. It's the so-called joint research actions, and then it's the transnational access projects, which Mike already mentioned. And the joint research actions are such that where the IBISBA partners have decided in a way that how do we try to understand the bottlenecks, the sore points we have when we want to build the functional biofoundry, in particular from production strain design to process optimization. What are the laboratory tools, the computational tools, and which are the critical points in taking them into execution? An important thing is also the eTools platform where to develop for IBISBA, where we can do data management, we can pull out the operational project workflows and operate our business processes. And the transnational access, I just say a few words still, because these are interesting cases. They are true cases where academic or industrial partners come and ask for the project that can be carried out, or they want to carry out with IBISBA partners. And just to inform that there is a fourth TNA call now coming. Unfortunately, the deadline is tomorrow, but you can still, if you have a wish to have a biotechnology development work done with IBISBA, please look at the webpage. So also for IBISBA, as for anybody, of course, in the field now, the design, build, test, learn cycle of synthetic biology is important. And I don't go into details of that. You heard it from Paul. So it's very much relies on computation on one hand, automation on the other hand. And then automated data generation, and then making sense where I think we all suffer making sense of the data through computational tools. And in particular, if we think about artificial intelligence and machine learning, so the data amount, high quality data amount is the key factor here, which is limiting the efficient use of the cycle so that we can redesign the cells for better performance. So the data is the fuel. The more we have data, high quality data, the more we learn and the better we can predict. And putting the bioengineering in this cycle form actually shows that you can now have consecutive steps which follow each other, and it is also possible to make the workflows. But what very often in the Biofoundry developments is forgotten is that actually the organism which you develop needs to get into the process, the industrial process. And thus from the early beginning, IBISBA wanted to integrate the process development or upscaling into the design, build, test, learn upscale cycle. And this is why we actually draw the cycle this way, where we have the strain enzyme development going into design, build, test, of course, learn cycles, but scale up is an integral part where you learn also for design. And in particular, also this way, that you should probably take into consideration your design when you design your enzyme or production organism already, the constraints which may come from the process optimization and then the industrial process itself. For instance, maybe you want to do a techno-economic analysis in the first place to understand whether the oxygenation in your large-scale process allows actually to design a strain that would have the required yields and productivities that it would be cost-effective to make the product. And here then a little bit sort of dissected the different steps, still to emphasize that in the scale up, of course, you need to take into consideration the raw material choice on one hand, the upstream, and then the downstream processing, which actually are very good input already to strain design from the process side to think about how you design. Another thing which I want to make with this slide is that when we have these modules, I mean, these are rather big modules here now. So the output from the design is an input to the next phase. So we need to take care that the quality of the output, strain data, whatever is coming out, is good enough. The quality is good enough because it's the input to to the build phase, and in particular in a sort of integrated infrastructure where there are several partners, we have to make sure that this transition from one phase to the other is smooth and of high quality and no mistakes occur. So what we do then and have been doing is really to dissect the task in a way, one could say, dissect the tasks of what normally are biotechnical processes that are needed to carry out the services, computation and wet lab. And this is for two main reasons. One is that with this way, we can make hierarchical structures of the modular tasks. And these can then be combined in a desired manner for a particular project to make the seamless workflows. And there's a lot of sort of generality in biotechnology, so you can really pull different modules together irrespective of the product in question. Of course, I mean, you need to care about that as well, but to have the modular task this way. And it's also important to have this hierarchical structure so that you can trace back experiment in a systematic way. Another important thing is then that only by doing this, you know where you really need harmonization in the procedures or harmonization on the protocols. You don't always need it, but there may be some critical points where it becomes a quality criterion for transition between the partners or transition between the different task modules. And we carry out then this with experimentally and computationally for relevant parts and do some round robin. And we have internal IBISBA internal cases like metabolic engineering done with Saccharomyces yeast and Pseudomonas bacterium from design to process, strain design to process scale up. And very importantly also, we have these transnational access projects from external clients, which provide then additional workflows, additional species, different types of products to consider. And this is an example of a real TNA case from an SMA company. So that was protein production with yeast. This is, one could say that this is rather from the simpler side of the cases. But still already this is an illustration how protein production, which is not typically considered the design, build, test, learn case so much, can be actually, the steps there can be put into this overall task model cycle. This is also an example where we could say that we have three partners. There is the client and there are two IBISBA partners carrying out the project. So the client designed the new promoters, which drive the expression of the protein product. They built the production strains or the strains to be tested. And also they did high throughput screening of promoter variants, how they perform in microtype cultures. They did not have the capability to go then for bioreactor cultures and not to the pilot scale operations. And this was then partner one from IBISBA, that was University of Barcelona, did chemostat and small scale batch cultivations to analyze the optimal conditions for each of the promoters, optimal external conditions. And this was then transferred to partner two, who was ourselves, VTT, who had the capability to go into even pilot scale production. And an interesting learning from this experiment was that even though both partners, IBISBA partners, were experts in their field, so the ways we measure things and the ways we calculate things are different. And this then creates not obvious understanding in a way what the data means. And this is a clear place for harmonization, even though it may sound trivial. And these you can only sort of figure out when you actually work together and when you do the work. So with these exercises, then we have been pulling out sort of the task modules. So here is design, build, test, learn, upscale, scaling up experiments. And we have opened up here the test in a way showing that you can have the generic sort of modules, task modules for doing a test with analytics and bioreactor culturing and so on. And you can then link here protocols and computational tools. And this is an example where we show what kind of tools can be linked into the whole cycle, the computational tools, and then the wet lab experimental tools. And gradually more and more, then the aim is that we can have fully integrated and parts of this sort of automated workflows to do the project over the, spanning also the capabilities of the different partners in IBISBA. Collaboration is important with other S3s, other European level infrastructures. One is of course Elixir, which is dealing with making computational tools for biosciences and also data management tools. And obviously also there is interest to collaborate with other consortia in the field. So what IBISBA then would have as a whole, or is beginning to have, is that we have the services, the service catalog Mike was saying, where it's not only the design, build, test, learn cycle, or let's say that we can carry out the whole design, build, test, learn cycle, but the customer, the client can come in just wanting bioprocess development or extensive analytics, or just screen for a new enzyme. The wishes of the customer would then be sort of looked upon our sort of universal task module hierarchies, and those relevant for that particular project would be then pulled out, linked together, and maybe some parts of that project could be carried out through automated workflows. The customer then gets the report out of this, and of course IBISBA uses its all know-how, but also learns a lot when doing this of the biology, but also importantly, we learn how to smoothly operate and how do we can have sort of a good quality operation of the project executions. So my last slide is here, and I think we all hopefully share the vision that biotechnology, synthetic biology, biomanufacturing will be in greater and greater demand in the future, and the capabilities are needed. It is because biology, biotechnology really inspires, and we know that it can provide sustainable solutions for the future if we can just make it more efficient. SMEs are very often sort of the innovation drivers here with their nice ideas, but they generally do not have sufficient in-house resources to carry out all phases of the project. Then we have the bigger companies who have quite a challenging job to transit from fossils to renewables, and they need support. And very much this need for support comes also from the fact that if you do not have insight into biotechnology yourself, so biology looks really complex. And it's not very much help that the literature is so diverse with different non-standardized protocols which have been used, and also often the data may not be quantitative and not of good quality. On the other hand, then we have the sort of promises of synthetic biology and automation to make biology really engineerable. And I think we have good cases to say that this is happening and this will happen. And we also know that in particular, this field is moving very fast forward. So if we think of academics or companies, big or small, so it is really important for them if they enter to biotechnology or want to have cost-effective processes, that they use cutting-edge capabilities to really have cost-effective research and development programs and speed up the time as well. So this is where then IBISBA wants to sort of bridge the need and the capabilities with building this unique operational platform. And of course, while doing this, we have a mission to really be a strong player and also a good collaborator to take the biotechnology acceleration forward in Europe, but of course also globally. So thank you for listening. This was my story.
Thanks, Mircea. We have a couple of questions coming in. First one is more, I would say, administrative, but probably important for future partners for IBISBA, is how do we go about dealing with IP and the different regulatory issues when we have these multinational collaborations? I don't know if you can give a few words on that one.
Yeah, I don't know, maybe it's more for Mike being the coordinator, but I think we have quite good models also within the partners, how we may do that. And this is an investigation at the moment, which we're carrying out in a way, which models would be good, because obviously if we are working with industries, we need to have quite clear rules who shares and or who owns what, and then there may be different approaches to the academic partners. Mm-hmm. But yes, we understand that yes.
Nick, if I can just jump in very quickly.
Ahead, Mike.
Michael.
Yeah, I can just jump in very quickly. So in the current situation, the current status of IBISBA, when we offer services like Maria just presented, where there's two partners, each partner has its own rules for dealing with IPR. Of course, the objective of IBISBA in the future is to do better than that. And so part of our aim is to actually make sure that in the future we can align different partners so that we have a similar sort of outlook on handling IPR, and that will be fully possible when we get to the stage where we actually create a legal entity which can deal with these multi-service contracts.
Okay, thanks, Mike. We have another question coming in about how do we consider the downstream, the raw materials, industrial constraints. But I would suggest that we revisit that question after the next presentation, which is going to be more concentrated on the scaling of the processes. So if you can remember to switch off your screen then, Mircea, and then thanks again for that really good talk. And we'll move over to our next speaker. And this is Katja Patsch. I'm hoping I pronounced that right. I'm not too good on the German pronunciations. But she's a biochemical engineer by formation and has been working for quite some time now in the Fraunhofer Institutes, which of course are very industry facing. And this is where she's been developing the biotech aspects, dealing a lot with the different scaling aspects of industrial biotechnology. So I think this was going to give us an interesting counter talk to, how do we consolidate this process development side with the very, very high throughput strain engineering systems we can do today, and then the advantages and the problems that can eventually pose. So Katja, I'll hand you the parole straight away. The floor is yours.
Okay, now my audio is on. Hopefully you can hear me. I'm sorry. So, Nick, thank you for the kind introduction. I welcome you all to our webinar today. And yeah, I want to talk about process development and especially scaling up, because this is really a critical process step to make processes with industrial sense, so that you really can go into industrial applications. The Fraunhofer CBP is a pilot platform in the Fraunhofer Society, which is the largest research organization in Germany. And yes, I directly want to start with the design, build, test, learn cycle, as Maria mentioned before, and our view to this cycle. So what is the aim? What we are working to is to really have a process with robust trains, which aims in robust process development, optimization, and especially scale up. What we need for this, so maybe this is also one answer for the question from the last talk. We go into the design block with different questions. What is the strain? How we have to cultivate the strain in the seed train, so the pre-cultivation. What kind of media substrates we have to use? What is a fed batch model, or is it a batch model? And also the DSP steps we all design first, before we then go to implementation of this setup. So this includes then automation of control parameters, and also to connect or install all the equipment we need to really test then the process. This could be fermentation, cultivation process in bioreactors. This could be a biocatalysis process, including always with the product recovery and purification. And then, of course, we want to learn by this tests. How is the performance of the process itself? How is the performance of the strain? What is with the product title, yield, and also purity and scalability are questions we have to answer within this TL cycle. And this will then go back to maybe to lab scale or to strain development. So what are we doing here at Fraunhofer CBP, or what we want to do also in the IBISBA project? So normally a lab scale developed process is coming to our facility, which has a technology readiness level between 2 and 4. Then we start to go into a technology transfer to evaluate the process, to get some information about this, to define some protocols, and also to define the automation control systems we need. And then we go to the scale up later on, hopefully to a demonstration. And then the really aim is to have the process available for manufacturing in large scale. And the big issue or the big challenge is really to identify and handling bottlenecks in the way of industrial processes. And here I want to show you a little bit what are the challenges. So we always ask the question, what have the partner in mind during the process development and lab scale? So you can scale up a shaking experiment in large scale. You always have to think about steering systems and so on. And it's also very important to think about a later facility in an industrial plant. One big issue in Europe is the regulation on GMOs. So often we have the problem that one microorganism is BSL level 1 in some countries, and in some countries it's BSL 2. So how we can manage this difficulties within the European world. And then, of course, what are the process parameters within, for example, the fermentation? So we always asked the partner or the client how to control the oxygen supply. This impacts the growth and the production of the strain, of course. how you deal with the feed rates, if it's a fed batch or continuous process. So usually if you scale up a process and you have larger scales, then the feed rates are limited in certain areas. So you have to be careful with this. And also one thing is how to use, or which kind of antifoam you have to use. There are a huge amount of antifoams on the market, but not every antifoam is feasible for a big scale, because you are not working with small tubes or glass bottles. You are working with stainless steel facilities, and then you may be running into cleaning problems. And also, at least the scale-up criteria is very important. This depends on the microbial itself. So we heard about filamentous fungi. You can use power input for filamentous fungi. You more have to take care of the tip speed or something else. So this will maybe make your process a success or not. And then also we asked if the partner really take care or observed the restrictions on industrial plant. So as I mentioned before, we are not working with glass or with plastic bottles. We are working with stainless steel plants. And here it's really important to take care of in type of corrosion. So media components, acids, high temperatures, or what else can be difficult to use in stainless steel plants. A second part is also the cultivation medium. In lab scale, of course, you always have to do or prepare different bottles. You have some stock solutions. You just mix everything together and then it's fine. But if you have a cultivation medium with 6, 7, 5 or 10 fractions, then it's really hard to prepare this cultivation medium in pilot scale or in big scale. You don't can handle so much flask. You have to handle with vessels and also stainless steel tubes, and this could be a problem. So our aim is keep the cultivation medium as simple as possible. Also very important is wastewater management. This is of course specific in every region, but in Germany we have a strict regulation on this, and here you always have to have in count. You can add high concentrations of heavy metals within the trace elements, or antibiotics, which are temperature stable, or too much phosphor or nitrogen sources. So you don't think about this in lab scale because it's not a high amount, but if you scale up until 10,000 liter or something like this, then this is really to handle carefully. And also what Maria mentioned before, one aim is not lost in translation. So really, it's a difficult thing to really use the technology description of the partner. It could be just a protocol from the lab, and put it or transfer it into a real handleable protocol in a pilot platform. And later on, also in the manufacturer, they have batch records. And so this have to be in one way so that everybody knows how to work with it. Really, a big issue is downstream processing. So if you have high performance strains and if you have a really good fermentation process, you are not on the end of the process development, because the downstream processing often don't have this attention at the clients. So the downstream processing steps are mostly the cost-intensive steps, and also you have here mostly high product losses, could be. So you have to be really careful on downstream processing steps. And also what kind of technology for the downstream you are using. Yeah. So only one experiment or one example. If you have purification of enzymes, then in lab scale you maybe use heat precipitation of enzymes. In lab scale this is fine, because the heating and cooling down is really fast. But if you could scale it up, then you don't have minutes or seconds, you have hours. And this is not really feasible in large scale. So you have to think about in the lab scale, is it scalable for later on? and also the technology description of the customers are often not really representative. So often we have to ask for how long we can store the fermentation broth overnight, for example, or if you have to run it continuously in a night shift. Yes, and often the calculated data or calculated duration of the DSP is a little bit too optimistic. So we often have, yeah, it's a challenge to really prepare this in pilot scale. So again, when we go through this cascade of scales, so I would say, we always have the loop back to the scale before. So if we have a technology transfer and we've saw some problems, then we play it back to the lab scale, so that we can really learn from this technology transfer and go back to development for the strain or process in lab scale. And this is the same for the scale up and demonstration phase. Always, if there is an issue we have to optimize, then it will go back to the loop before. And the real aim, or what we say to all customers, please think about industrialization already in the lab development. This is really important. And always have in mind, all steps of your process have to be scalable. You have to pay attention to chemicals, waste, because this always means costs. Just some words to the Fraunhofer CBP in Germany. So we are a pilot facility really to go from lab to industrial scale. Here we have the combination of pre-treatment of substances, a combination of biotechnology or chemical transformation, and also the downstream processing as part of our development. So that we really want to go from lab scale to industrial application, and to support clients in this field of process development. And one big issue what we offer at Fraunhofer CBP is that we can go to the fermentation cascade up to 10,000 liter, and with this scale, it's possible to really provide samples in huge amounts for technical application tests, for example. So transnational access within the IBISBA, Maria and Michael mentioned it before, is a program where you can get access to our IBISBA infrastructures and capabilities. For example, the infrastructure at Fraunhofer CBP for the fermentation cascade. You can get support for process development and scale up. And also you will get preparatory data for industrialization of your process. So design, build, test, and learn within IBISBA is to create successful processes within the industrial biotechnology. And with this, I'm at the end of my presentation, and I hope maybe you have some questions.
Thanks a lot, Katja, for this one. I'd like to push you a little bit to stretch you. You said it's good that we feed back into the lab level so that we're ready to make it easier to scale. Are you willing to go a bit further than that and say, really, if we got some idea of the process at the end of the day, we ought to be feeding that back into our strain design. So we're developing a strain which is capable of resisting the sort of pretty intense stress that you sometimes get in industrial fermentations.
Yeah, that's right. So sometimes you don't have the time to go back to the lab because some clients really go forward directly to ton scale, and it's always challenging or for us to really discuss this issue with the client, that it would be better to go back to the lab and really develop a robust process and then go to the scale up again.
That's great. Yeah, we're probably going to come back to that in the round table at some point.
Yes, please.
I think it is a key point. So thanks again for that sort of insight into the scaling aspects. And I've seen that Sunil has actually joined us. So good morning, Sunil. Back, it must be early morning over there in the West Coast. Huh? So yes. You can de-share your screen catcher so Sunil can upload his presentation. It's so whilst we're sort of switching over the screens, let me just give you a quick introduction to Sunil. We thought it would be good to finish off this sort of open session with a real pioneer vision on industrial applications as from Biofoundries. And one of the early movers in this domain was clearly Ameris, who sort of was almost a pioneer, as we saw in one of the previous slides from, I think it was Paula. And Sunil has been working, he's now Senior Vice President of R&D at Ameris, so he's the guy to talk to. He can give us the info on how the Ameris Biofoundry is developing and how that's enabled them to bring products through to market, I think. So if you're ready then, Sunil, the floor is for you.
Thanks a lot, Nick. And first of all, thanks to all the organizers for this invitation. It's been a long time coming to get this conference together, but I'm glad we could all do it. So, yeah, good morning from California. Yep, it's bright and early here. So what I'm going to talk about is, I'll talk about the Ameris Biofoundry, but it's going to be in the context of an entire pipeline. So because Ameris is, as a company, we can't just focus on strain engineering. We have to focus on actually taking a product to market. And the Biofoundry is what I would say one of the technology platforms that allows us to take that product to market. So I won't go into details of strain engineering or analytics, but really talk about how all these different tool sets fit into a single platform that then have to be thought about in context of taking a product to market. So with that, let me just get started. So what we do, I think a lot of you know this, our business model relies on transforming sugar into pure ingredients using yeast. Now, every molecule we have produced at scale today has been with Saccharomyces, but our Biofoundry, of course, has had to evolve and start incorporating other products, incorporate other hosts to take different products to market. And let me just put on my pointer here. So a quick introduction to Ameris. So we are about 600 employees now. We're located in the San Francisco Bay Area here in California. Out of the 600 employees, about 250 are in R&D and process development who actually deliver on the projects. We manufacture about 9 different molecules at scale. And these 9 different molecules now are present in greater than 3,500 brands across the world. In some form or the other. Now, this is a Biofoundry talk, but you will hear me talk a lot about manufacturing, and it's important to talk about manufacturing from the industrial standpoint. And so, with that in mind, Ameris has access to over 1 million liters of fermentation capacity, and we have, of course, because we manufactured so many different molecules, we have extensive scale-up experience. Today, if you come to Ameris, we'll talk about having about 20 new molecules in commercial development. And the goal is to launch 2 to 3 molecules at scale every year. And so when you think about that, 9 molecules manufactured at scale, 20 molecules in commercial development with 250 people in R&D, obviously we had to do something different because there's no way to handle that many molecules with that many people. And so we had to invest differently in different areas, and we had to do this starting back in 2009, 2010. And so today, what I would say is that 3 main areas where we really invest our R&D resources in terms of technology platform development. So the first one is, of course, cellular programming. Now, when we talk about strain engineering, we've been used to, from grad school, for example, we are used to, cloning a piece of DNA into a plasmid, taking that plasmid, transforming it into a strain, and then checking if that strain works. For us, very early on, we realized that couldn't work because the number of permutations and combinations in biology was just far outstripped the ability to test those strains, to build and test the strains. So we had to change how we were programming ourselves. And so this involved assembling a huge number of DNA cassettes simultaneously, transforming all that DNA into the strains. Enzyme engineering. Every project we have worked on at Amyris, without, and this is without exception, every project has required at least 1 or 2 enzymes that needed extensive optimization, either to increase activity or to increase specificity. And so when you take all that into context, we just had to figure out how to modify cellular DNA and add that functionality to the cells. And so today, the biology team will send on the order of 1.5 million strains over to the analysis labs. And so now that results in a new bottleneck, right? And so the other point I want to raise is every time we have solved for one bottleneck in a biofoundry, we have created a new one. It's just inevitable. And that's something that you just have to keep thinking about in your planning cycles, that I'm solving for this today, what bottleneck is going to create tomorrow? And so when we started solving for the cellular programming part, what we realized very quickly is our testing platform now had to keep up with all the strains that we're building. And so, and it wasn't just test the strains, look at the data and be done with it. Really, we wanted to collect rich data. We did not want to treat the cell like a black box. We wanted to understand everything that was happening in the strains we were producing. And so we had to develop analytics platforms that collected high throughput rich data that allowed us to understand, here's what we did to the strain, okay? And here's the data that is now generated based on those strains we have built. So that's great. Okay, what's the next bottleneck? Well, you have now generated all this data for millions of strains. How do you analyze all of it? Because again, in 2010, trying to understand how cellular metabolism works was still very manual. And so what we had to do is represent the cell computationally, or in other words, start coming up with better computational models so that you can take all this data that we generated from the analytics platform and then overlay it on top of computational models or statistical models and try to understand really what happened. This is what I did to the strain. Here's what the data says. So what really happened and what should I do next? And this is definitely an area that is still something that we are still trying to figure out, because again, biology is so complex that it's naive to believe that we can just apply machine learning and know everything that's going on in the cell. But we do apply a huge amount of statistical models and some machine learning to understand, okay, from all these millions of strains I built, here's the data, and here's what we need to do next. Let me now, so this is now what the Amyris R&D and process development pipeline looks like. And so you'll see that I'm not just talking about strain engineering here. There are many different components over here. So starting with automated design, again, if you have a biofoundry which can build thousands and thousands of strains a week, you can't do that with manual design tools. So we had to build tools that allow the scientists to rapidly design strains that could then go into the automated strain engineering platform. Now that's the original, when we talked about the Amyris Biofoundry, I think that's what a lot of people have heard about, the automated strain engineering platform. And so that is definitely one component of the pipeline, but now we have combined that, integrated that with other platforms. And now you have the high throughput screening platform, the high throughput fermentation, analytics, and last but not least, and probably the most important part of the pipeline we developed is the manufacturing, because everything that you do on this part of the pipeline has to feed into the manufacturing, because if this is unsuccessful, it doesn't matter how good you are over here. Now, again, this is with respect to a company where the Biofoundry is not the primary business model, it's actual product. Okay? At every stage in this pipeline, what we're doing is continuously capturing the data and trying to get better at every step. So for example, if your assembly rate in the strain engineering platform is low, why is that? Okay, was it because there was some systematic error in one of our instruments? So you have to make sure that you're capturing not just process data, not just the strain data, but also the process data to make sure you keep improving the pipeline and keep moving products to scale. I think I wanted to also highlight this part, human intelligence. I think we've all gotten so caught up in thinking that big data and machine learning will solve all our problems. And and don't get me wrong, it's a huge part of what we do, but you cannot discount the power of human intelligence, because at the end of the day, you still need scientists to really make sense of everything and then start pushing things along also. Let me just give a quick synopsis of each of these different phases in our pipeline. So let's start with automated design. So in automated design, what we're trying to do is find the optimal biochemical route from sugar to target molecule, and then translate those routes into DNA design. And you've heard plenty of talks that deal with this. We have a slightly different approach, but again, this is something that a lot of people do. So what we have done is, like a lot of other labs, is we've built our own computational model that essentially catalogs all the reactions that could happen in a cell, and then what the genetic elements are behind those reactions. So today, if I had to figure out how do I make a certain molecule from sugar, I can rely on the databases we have, on the computational tools we have, and we have what we call automated pathway design. So again, in grad school, I would have had to spend weeks trying to figure out what the optimal biochemical route is from sugar to a molecule. We have systems that do this in a matter of minutes. Now, this was easier said than done, because you can imagine that when we first started doing this, a computational model will simply give you the shortest path from sugar to the molecule. So instead of 19 reactions, it might figure out, okay, I can do this in 5 steps and give you a pathway that looks really efficient. But then when you dig into the data, into the model, you start realizing that it's picking reactions that are thermodynamically not possible. Maybe it's picking an enzyme that actually works in the opposite direction. So this took a lot of time for us to optimize and tease apart, so that instead of giving us the shortest path, it gave us the most possible route. Again, is this perfect? Not yet. We are still working on it, but it definitely does a great job of helping us understand what is the yield of that molecule from sugar, because this yield then sets the theoretical limit for what we can achieve at industrial scale. So, for example, in this example, what it's saying is, for every 100 grams of sugar that I give to the cell, only about 24 grams of that sugar will get converted to product. And the target here is, of course, pharmaceutical. And so if I think of, okay, if I take this to industrial manufacturing, what is the overall cost of my manufacturing? Well, that just sets a theoretical limit on that. So this is an important part of the Biofoundry that we run. And then, of course, on top of that, okay, great, you now have a tool that allows you to tease apart the pathway. How do you now translate that into an actual design, or an actual genotype? And so we had to speed up the design process, and we developed what we call the genotype specification language. We published a paper on this, and it's really a programming language for DNA. And I think the logic here is, computer scientists, when they code, they don't code in zeros and ones, right? They will use a programming language like C++, Python, PHP. So why should biologists code in ATCG? There should be an easier way for us to write DNA. And so we came up with this, what we call GSL. So a simple instruction like this, and biologists could easily read this and say, yep, you're deleting the RTC2 gene, and you're introducing GAT1 and BIC1 with the TDH3 promoter. But this is easy to write, but the software can easily decipher this and quickly figure out the sequence and the entire assembly of parts that's needed to build this cassette. And so again, in 2008, when we were doing this as a company, we were doing manual route finding, manual DNA design. So coming up with 20 designs would take us weeks to do so. In 2018, we optimized this to 1,000 designs in about 10 minutes. Okay, and so this is one, of course, now this then results in the next bottleneck, which is how do you build all that DNA? And so this is where the automated strain engineering platform comes in, which translates those computer design DNA into physical DNA and then introduces the DNA into microbes. And so again, the old standard, this is back before we built our ASC platform. And this is how I used to do things too, right? So you design the idea, it's manual curation, you do low throughput, high cost DNA assembly. And so this is using old cloning methods or single assembly methods called stitching, and then you engineer the strain, and then you get one product. But really, what we are trying to do is create thousands of designs in minutes, and then you make thousands of low-cost, fully sequenced DNA assemblies every 2 weeks. I'm highlighting that fully sequenced for a reason. When we started building Biofoundries, in the initial days, we focused entirely on throughput. Okay, and our belief was if you just make a huge amount of DNA, it'll solve for everything. You have to keep sight of the fact that throughput and quantity are meaningless if they're of low quality. And so you have to now figure out a way to intersect quantity and quality so that you're not just throwing junk at your strains, you're actually producing high quality, fully sequenced DNA assemblies. And so I would argue that the quality was more difficult to solve for than the quantity. And then of course, once you have the thousands of fully sequenced DNA assemblies, you can now create thousands of verified strains. So again, if you're building these strains, we need to make sure that they are the right strains and not just something where integration has gone wrong and the DNA is actually not in the location you thought it was. And so that's what we do. Okay, the next step now, okay, thousands of verified strains generated per week. We need to analyze all of it. Now, this is where in 2015, we could analyze maybe 200,000 samples a year. And this slide talks about a very specific problem that we had to solve for, which is how do you do high throughput metabolomics and proteomics on the strains you're building? Because we could focus on just measuring the titer of the final molecule, but then you're missing out on everything else that's going on inside the cell. And so again, in 2015, if you look at the workflow, we had to figure out, okay, what method are we selecting for a specific metabolite or protein? That took some time. Sample preparations which is what took the longest time. So preparing samples for metabolite and proteomic analysis took a huge amount of effort. And then of course, acquire the data and then data processing. And so what we had to do then is switch things around. And in 2018, we came up with a workflow where it took us about, so in the previous workflow, 2 hours per sample. Today, we are slightly better than that. In 2018, we developed it for 4 hours for 96 samples. And really what we did is, there's a huge amount of data as to what methods work for which metabolite, what methods work for which protein. There's no reason why we had to keep manually curating it again and again. And so we came up with a simplified automated method predictor, which essentially predicts the method for a given metabolite or protein in a matter of seconds. The big one, of course, was automated sample preparation. And again, for metabolites, you have to be able to quench your samples in a matter of seconds. And so that we've figured out a protocol where we can do 96 samples for metabolites in an hour, for proteomics in 3 hours, and then data acquisition and data processing. So what this does is helps shrink the entire timeline to actually get rich data sets for your strains without losing on quality and without losing on the throughput. Let's get into now what we created the next bottleneck, which is great. You're building all these strains, you've analyzed it. At the end of the day, remember, I have to take this to manufacturing. Manufacturing is at the 200,000 liter scale, 500,000 liter scale. There's no way to test thousands of strains at that scale. So what we need to do now is figure out how do I test these strains in the lab setting and predict how these strains will perform at scale. And so we have to redefine this process. So this slide, essentially encapsulate what the problem is, because on the right is where we need to be, right? This is a 200,000 liter scale. It's a highly controlled environment in a large scale fermenter. You're continuously taking readings and you run one strain for 2 to 3 months. And then on the other side of the spectrum is your lab scale, because now you're trying to do this 100 microliters. Okay, you're just adding sugar once. It's a small 96 well culture plate. You're taking 1 to 2 readings, over 4 or 5 days, because you just can't take that anymore. And you're testing a lot of strains. You now have to figure out how to translate these results into this. And so you now have your intermediate steps, which are your, for example, the 1 ml or the what we call the biolectors, and then the what we call in the labs, we call it the standard, which is a 0.5 liter or 2 liter fermentation labs. But again, you can see the difference in throughput, right? So you need to scale, you need to start testing hundreds of thousands of strains per month, scale that down to 200 strains per month, and finally 50 strains per month. This is now where you can really start testing scale down models of your manufacturing, but you need to figure out how to weed out the bad strains from here. And so we spent a lot of time on this. This is where a lot of statistics comes in, where you need to figure out what are the different assays and measurements you need to do to predict manufacturing scale performance from the lab scale. And so this is one of the examples for one of our products that we've taken. Again, this looks very nice. Now on the x-axis is the performance that we predicted, is the performance we measured at lab scale. Okay, and on the y-axis is the performance for that same strain, okay, at manufacturing scale. did this happen all at once? No, this took many years for us to develop. Okay, but our experience in taking so many molecules to scale allow us to rapidly predict how something will perform at the manufacturing scale based on large scale results. So this is my last slide now. So really what we have done is it's a biofoundry, but what I would call it is a pipeline. And it's a pipeline that is that was built with fast time to market product design with the end solution in mind. Okay, and so I talked about how the ASE platform enables that to happen, but at the end of the day, this is what really matters, right? So for example, let's say we have a project where the business team comes to us with a molecule in mind. Okay, so let's call that month 0. Okay, we do the pathway construction, all the database queries we need, figure out the cost analysis, figure out, okay, is this molecule possible or not from biotechnology? Because that's the other thing we never talk about, which is it always possible to make a molecule economically using synthetic biology? Sometimes the answer is yes, sometimes the answer is no, but you need to understand that before you embark on a large project. And so we have to do that analysis upfront. And so you do the cost analysis, feasibility. Okay, if it's feasible, figure out how the biology is going to work, start building your strains, and that's what we call the strain optimization part of a project. You call that, so that takes anywhere from 0 to 9 months. In that time, you're also doing your process development and analyzing those strains. Now, during that time, if you start seeing strains that are actually making a molecule in decent amounts, you can start going to pilot plants. Now, what does the pilot plant mean? Pilot plant is at the scale of about 300 liters, okay, 300 to 1,000 liters. And really, why do you need that pilot plant? The pilot plant is needed because this is where you will actually start generating some material. This is not industrial scale material, but you generate, let's say, a kilo of material that you can then deliver to your business partner so that they can start testing in their formulations, or it's what you use to get regulatory approvals. But today, what we can do, so if you go from month 0 through strain optimization, analytics, process development, pilot plant, recovery, at Amyris today, for any project that we work on, we can go from month 0 to month 12 and deliver 1 kilo of that material. Okay, so and so that is significant because it has accelerated the time to market, because you can start the regulatory process before your project is even complete. And in fact, your partner can start formulating and testing your product from your fermentation facility in a year. And that's a big advantage for the partner itself. So again, in summary, over the last 10 years, we built our first fully functional automated, it's an automated engineering pipeline. I wouldn't call it a single biofoundry. So what this has resulted in is, again, with a team of 250 people, we are able to make a lot of progress. So this has resulted in, of course, a 10-fold lower development cost for new molecules and a 5-fold reduction in development time. I talked about this 9 molecules at scale, and we currently have 20 new molecules in the active development pipeline. So with that, I'd like to thank you for your attention, and I'm looking forward to the panel discussion. Happy to take questions as well.
Yeah, thanks, Sunil. That's a great example, I think. We've got a few questions coming in. We'll try and squeeze a few of the questions in. Some of them may get pushed back to the round table. But to begin with, we've got a question on how does Amyris cope with EU regulation restrictions on GMO-derived products? Suppose it's a problem you try to deal with virtually every day.
Yeah. Oh, yeah. Oh, great question. Yeah, it's something we deal with every day because a lot of our products are sold in Europe. And so we have a regulatory team that works very closely with EFSA, and we understand the regulations in Europe. And then essentially it's a conversation trying to explain exactly how our process works. A lot of times, the concern is, does the product actually contain the genetic material that was used to generate the molecule? Okay. And so that is something that you have to be very transparent about, and your analytics team has to provide the necessary data. So we have to show that there's no protein, there's no DNA, there's no hint of a microbe in any of these products. We also have to make sure that the sugar source, so a lot of times the regulatory bodies will look at the sugar source that you're using, not necessarily the host, because the host itself is a catalyst, and the host doesn't make its way to the final product. But you have to make sure the sugar that you're using is not from a GMO source. And so these are different aspects that we have to look into when we go into a project. Great question.
Okay, another one to follow up quickly then is, how do you manage the false negatives that come through your screen? Or do you manage them, or?
Yeah, I mean, the false negative is, I mean, I would say false negative and false positives. I mean, so false positives have a tangible impact, right? Because you're sending strains to the fermentation lab that never should have been sent. The false negative is a good one because you don't know which strains you are leaving behind. And so this is where there's some oversampling that you have to handle. Your pipeline has to be able to do that. The way we also get around false negatives is we don't rely on a single measurement model. So we rely on multiple measurement models. And if a bunch of strains, for example, look good, surprisingly good in one model, but not in the others, is that a sign of a false negative, right? I mean, the analogy I always give is, you are trying to find the best marathon runner in the world, but you have a 100-meter sprint to find them, right? So then in the 100-meter sprint, how do you find the best marathon runner? Well, you maybe run many different tests during that time. So it's not easy. The false negative problem exists. We've tried to solve for it through many different ways. So, but yeah, good question.
Okay, we did have a third one on the way you downscale your fermentations, but I think Mike intends coming back to this in the round table, so we can perhaps we can discuss that in a little bit more time during the round table than we've got at the moment. That's the ones I've got coming in at the moment. So thanks again, Sunil. I think there's a great talk showing how industry is dealing with it. It's always nice to see that it is giving the product flows coming through the end of the pipeline, which is the essential. For that, I'm going to close the actual sort of active session of invited talks now. We're going to give a quick, brief bio break, and we're going to restart again on the round table at about 4:15. So please just don't go out of the conference and then have to have the delays coming back in. Keep it open, and then we'll reconvene at 4:15. Start thinking already about the type of questions you might want to pose into the round table. That way we can try and take them into account if time allows as we go through the prepared questions, but we want to leave some time for the more open questions as well. So I see you all again then in about a little bit more or a little bit less than 5 or 10 minutes now to begin the round table. Thanks again to all the speakers. It was a really great session, and hopefully that'll continue in the round table. Bye everyone, and see you soon.
Okay, so it's 4:15 here in Europe. So we'll start up again as Nick indicated when he left off. So I'm taking over now for the panel discussion. And actually, Nick, you've changed places because you're now going to take part in the panel. And maybe to start the panel discussion, so I'd like to introduce 3 other people who are going to be in the panel with our previous speakers. So Nick, maybe you can kick off by just telling us a couple of messages about yourself and maybe why you've changed places and have now integrated the panel discussion. You need to put your microphone on, Nick.
On mute. So a few words of background. You know, I was trained as a microbial ecologist originally a long, long time ago, and then gradually moved over to pathway engineering, and we began our team in metabolic engineering in 1991, and attracted by the fact that metabolic engineering was a knowledge-based, rational design. And then we discovered very, very quickly that the amount of knowledge was largely insufficient to do rational design, and then gradually moved over to these more combinatory genetics type approaches. So I worked on that for a while and then took over the overall running of the Toulouse, what is now the Toulouse Biotechnology Institute, for about 12 years. And then in 2015, took on a new challenge to actually build up a consolidated pipeline in Singapore, looking at the sort of high value ingredients which reinforce the idea that you've got to have these high throughput platforms to get things to work. When you're looking at adding 1 or 2 enzymes into a strain, it's pretty simple. When you've got to branch in a 20, 25 enzyme reaction chain into a chassis organism, it becomes intensely more complex to get the pathway design. So that's sort of the way I come in. Now, why I'm now part of the panel is because we've been playing around with this Biofoundry approach, mostly from the Singapore side. So we have a little bit of experience to share on why we think Biofoundries make our life both more expensive but easier. Yeah. So that's the intro. Yeah.
Okay, thanks, Nick. Now, I could maybe ask Vitor to present yourself. So Vitor Martins dos Santos from the University of Wageningen.
Yeah, so good morning, afternoon. I'm Vitor Martins dos Santos. I'm actually a chemical engineer from background, and I moved with time to genomics and systems biology and synthetic biology, and I landed in Wageningen, where I run the Department of Systems Synthetic Biology. And we are really interested in reprogramming microbes for production of fine chemicals and increased robustness. So we're really interested in contributing to a real shift from the petrochemical base to bio-based economy, and we think synthetic biology it can really make a difference here. And we are obviously very interested in biofoundries and on connecting experimental and going through all the iterative DBTL cycle, coupling experimental and computational edit designs. So this is part of our interests. We are part of the IBISBA, and this is the panel discussion I'm very interested in.
Okay. And to finish the new guests, Olivier Roland from Toulouse White Biotech. Olivier, a few words about yourself.
Hi everyone. So yes, I'm Olivier Roland, Managing Director of TWB. I'm a chemist by training, and I spent the last 10 years in product development of biosource products. I actually worked with Sunil when I was at Total on the Ameris Total Strategic Partnership to develop the first sugar-based biofuels, and more recently, I led some innovative model to produce value chain in different parts of the world for sustainable aviation fuels. And I moved to TWB a year and a half ago.
Okay, so we've all understood that the theme of the afternoon is biofoundries, and maybe Olivier, if you can stay with your microphone open. Toulouse White Biotech and Biofoundries, is there a link?
Yeah, sure. So TWB is a public-private industrial biotechnology organization that basically transition early stage R&D into pre-industrial development projects as well as startups. And when you look at our projects portfolio, you could basically categorize our project in 3 categories. First one is basically developing alternative process to manufacture a given product. So basically substituting current manufacturing production facilities because there are threats like securing the feedstock opportunities or trying to decrease the cost of production. Second category of our projects is on basically accessing properties and performances that are not easily accessible or not accessible at all using standard chemistry, using biology. So biology has a way to get to these new performances. And finally, the third category of our projects are projects where our partners try to comply or to anticipate compliance with legislation and regulation that we put in place on with regard to greenhouse gas reduction emission. And so when you look at that, our partners base is basically ranging from partners who are highly knowledgeable in industrial biotechnology. So basically they come to us because they have a lack of capacity or they are missing a specific capability that we can provide. On the other side, partners who have no knowledge at all, almost, on biotechnology. However, they see biotechnology as a real way to grow their business, the real opportunity. And so when you look at this context, what we are doing at TWB is to set up projects to answer their needs, specification, by gathering internally and externally all the capabilities, all the skills, the expertise, and the equipment that are necessary to answer the needs. And so in a way, we are in this Biofoundry because we need the whole set of capabilities to go from an ID to a pilot facility for some of our partners, whereas we'll have to go and focus on specific expertise that they are seeking.
Okay. Vitor, you mentioned some of your activities in Wageningen. Could you qualify your activities in Wageningen as being around the Biofoundry concept? Do you have automated equipment and things like this in Wageningen?
Yes, in fact, because in Wageningen, one of the focus is really circular and sustainable bioeconomy. And that's one of the things that we realize that in many cases, all the biological processes are possible, but are often just not economically competitive. And we think that we need to have solid biofoundries and workflows that allow us actually to make a biologically viable process into an economically viable one. So that's why we've also been investing in aspects related to biofoundries and workflows precise to do so. And not only to single cells, but also for microbial communities. We just got a large grant as infrastructure for microbial communities to untap potential of uncultured microbes and microbial communities for parallel cultivation and unusual conditions precisely to be able to exploit that. And it's called Unlock, and so this is also one biofoundry for microbes. And it's really about combining workflows, about combining big data analysis and smart bioprospecting, transformation of trade transfer, and so forth. So for us, this biofoundries is really important.
Okay, thanks. I'd like to come back to Sunil. Thanks, Sunil. I didn't get the chance to thank you for your talk. Paul Fremont earlier in the afternoon pointed out that the Biofoundry concept and activities around Biofoundries now has been going along since, you know, for the most part of the last or the decade that we're in right now. I was wondering, do you consider that Biofoundries are now the key to serious business, or is it still in a too early stage to really talk about business game changer?
Yeah, the way I would frame it is it's an essential part of any business that we're going into today. The question, though, is whether a company needs to invest in that on their own, or whether there should be Biofoundry hubs that everyone relies on, right? I think when Amrith started this, there was no other Biofoundry. We had to develop it on our own, but it takes time and it's expensive. But is it useful? Absolutely. We have to get outside the paradigm of one strain at a time, one data set at a time. But I think I would definitely think about whether companies should be, new companies should be investing on this on their own, or whether they should be, investing in a hub where you can now access all these, different tools. So that's how I would answer that question. I think it's essential. I think this is how the industry needs to go to. Industry and academia, actually, both sectors need to head towards.
Okay, and maybe I'll profit while you're still on with your microphone open. There was a question earlier, which was about what is the fraction of new molecules to natural molecules that you would be targeting?
Yeah. So so far the molecules we've always gone after are, molecules that have been made in nature, or molecules where we believe there is an intermediate that could be accessed to biology that then gets converted through chemistry to the final molecule. So an example is the anti-malarial drug artemisinin. Okay, so artemisinin is a biological target, but making artemisinin through biology is still difficult, at least through fermentation. It's made in a plant, but replicating that in fermentation is hard. So what we do is we make artemisinic acid in a fermentation, and then we do the chemical finishing step from artemisinic acid to artemisinin. And so there are plenty of examples, and along those same lines, where you don't have to always solve for the entire molecule through fermentation. Sometimes even a natural molecule can be, you can access an intermediate and then finish it through some chemical steps. In terms of fraction, out of the 9, I would say, they're all biological targets, but I would say for 3 of them, we produce intermediate, and then those are converted to the final molecule through chemistry, organic synthesis. Yeah.
Nick, coming back to your experience in Singapore, I think there was quite a lot of investment in Singapore during the time that you were over there. I mean, what was the driver there for adopting this Biofoundry approach? Was it because you thought that it was going to be a game changer in the near future? Nick, put your microphone on.
Yeah, we moved quite dramatically towards more complex pathways, and we worked out the combinatorial, how many different strains you would have to be able to produce in order to get a good cover and do a sort of heat map of where the best pathway should be. And even working on a modular system in pseudo-operons to bring that down, it's still a pretty high number. And finally, you get to the point where your progress is being held back because of your manpower skills and your available lab space, and actually moving into a Biofoundry removed that bottleneck. It created other bottlenecks further down the chain, but it actually allowed us to test a much wider range and get to be much closer to a first step optimized pathway. And this changed the game completely. We have examples where we go from a few milligrams up to 20 odd grams of terpene type compounds in a 6-month period now. So it is, you're accelerating dramatically the speed which you can go from a good idea to something which starts to become economically feasible. So that was the logic behind it. Research in Singapore is very much industry facing. If you don't make money out of your research, you tend to disappear quickly from the scenario. And so it really needed, what were the tools we needed to put into place to be able to bridge that gap. And the Biofoundry was an obvious one. The metabolic engineering was good, and it required an accelerator to enable us to get to the final strains much, much quicker. Okay. So that was the logic behind it.
Okay.
It helps when you're in a country which is rich. Huh? Yeah.
Okay. Melia, I can't see whether our camera's on. Are you there, Melia? Yeah. Melia, there was a question earlier by one of the members of the audience, Anne Charbonnier, who was actually asking questions about how we see the process of actually capturing different industrial constraints, downstream processing considerations and that. I mean, how do you see we should be going forward in that area? How can we actually better drive these constraints? So, you know, manufacturing scale constraints into the actual early strain design.
Yes, let's say that often, I mean, of course, products which you can distill out. So, so then the downstream processing may be more cost effective. But then we have lots of new products coming out, which are sort of bulk products where you really need to use the raw materials, which are not sort of defined media, for instance. And there, then the challenge is really sort of lie, like, let's say, bioplastic precursors, for instance, where you have to have a certain purity. And I think if we would think about more, we would have I don't necessarily want to give all my ideas out here, but I think we could be more innovative of thinking in a way that how you could sort of think about how you modify, let's say, the raw material stream while the fermentation is, for instance, going on, so that the downstream processing would be more cost effective. And of course, then, I mean, any sort of innovations at the downstream processing side. And of course, we know that the even large scale processes, you can have these stripping type of product removal concepts and so on. But this would also need, and we have it in IBISBA, actually the capabilities or many partners who have the capabilities to think about the sort of balances between product removal and I mean, with various ways and what should be the titers in a way that this would be cost effective. You can, yeah. So this is one way. Of course, I don't know whether we need to, or whether this is a point to discuss about the strain robustness, in the sense that if your raw material is toxic, like a bioethanol case is a typical case where you do the pre-treatment and then you get the toxic compounds and low pH and so on. So there already comes also the question that how do you then know that you are going to be able to make an economic process? And I just want to state that, for instance, if we take Saccharomyces, so there are enormous variability in the tolerance, robustness of the strains. And also then if you go beyond Saccharomyces, so you have traits. So it's very good to have this kind of, let's say, process understanding, maybe yourself having done work on really real industrial raw materials, so that you understand in a way that what the organism actually needs to tolerate.
Okay, Katja, you're in a sort of an unenviable position in your CBP facility, in as much that you get probably quite a lot of clients who actually arrive with their strains already built, and you're the one who has to tell them that it's not going to work. What are the sort of typical problems that you're seeing with the transfer to the higher scales when it arrives on your doorstep in some way?
Yeah, the main issues are really the technology transfer of the process. So normally the client comes with the developed strain, of course, and then we have it in cryocultures or on plates or what else in our facility, and then take a look to their protocols and really to take care of the, for example, controlling mechanism. So how to control the pH, how to control the oxygen supply, how to control the feeding and the feeding rates. And often the challenge is that the feeding rates are really too low for industrial feasibility. So we have a range of feeding rates we have implemented at Fraunhofer CBP at our bioreactor cascade. And yeah, often the feed rates are too low, so that we have to be flexible. And of course, at Fraunhofer, it's possible to be flexible, but not at a manufacturer, contract manufacturer, so that we can implement flexible tubes or external pumps or something like this. But we often have this challenge really to transfer the protocol to our equipment, and then also to adapt it to the next stage that we can really go to scale up.
Okay. I was wondering, you know, following on from that, I mean, Sunil, in your pipeline, I mean, how are you dealing with these scale changes? And I mean, do you have any new thinking on this? And do you see any new technologies that have arrived recently that are helping with this?
Yeah, I mean, yeah. So I mean, scale up has always been the challenge. I think a lot of it is really understanding what your manufacturing process looks like. So I was addressing this in the chat session too, which is at Amyris, for example, we know what the manufacturing facility is going to be doing for that product before we even started with it. And so you have to try and figure out, can you replicate some of those conditions in the lab? Okay, so, and then you figure out what the scaled down model looks like. In terms of technologies that we need to develop, I think a couple of areas where I think investment is needed, you know, production of toxic molecules, for example, right? Can you alleviate toxicity of molecules through process engineering solutions as opposed to strain engineering solutions? I think that is an area that a lot of labs are looking at. We are looking at them too. And so that is one example of technology development that's happening at the scale level, where you are trying to produce something that just kills the host. So how do you now try and do a process engineering solution to fix it? The other one is around the downstream purification, right? So every molecule that is produced at scale somehow needs its own purification method. And these are not just one method, right? These are series of unit operations which are performed in series. So do you need to do that development every single time from scratch for a new molecule, or can you rely on past experiences? I think that area is still something that we are looking at. Can you accelerate that part of the process?
Okay, thanks. Again, I'm going to profit that before you close your microphone, maybe to go on to another point. I was really impressed with the numbers that you were citing earlier. You know, like I think I noted somewhere 2.4 million strains per year. Screen.
Those are samples, yeah. Those are samples, yeah.
Samples, yeah, yeah. You know, these are like fairly massive numbers. It could be seen when quite often when you consider biorefineries, it seems like a sledgehammer approach. I mean, are there any? Well, do you have any thoughts on that? And do you see ways of going to a little bit like in the enzyme engineering field, where we were using sledgehammer approaches until quite recently, and some people still are. But you know, artificial intelligence is kicking in that area. You mentioned this earlier, and Paul did too. How do you see, you know, more semi-rational, let's say, biofoundries in the future?
Yeah, I think it's so. The sledgehammer is a very good analogy. I think the sledgehammer approach, there's nothing wrong with it. It still works. It's an old technique, but it still works. You have to, however, I think, integrate that with a rational, semi-rational approach where, you know, you have some defined hypotheses that you then have to intermingle with your sledgehammer approach. So that's what we do at Amyris. I mean, 2.4 million samples, a lot of those are through some of our adaptive evolution or mutagenesis pipelines where we are applying that sledgehammer approach, but a lot of them are also through very rationally engineered strains. The enzyme engineering pipeline, we have an enzyme engineering pipeline where we exactly do that, the semi-rational approach, where we analyze the entire protein and try to figure out which amino acid residues do we believe need to be changed. But now here's where the complexity comes in. A lot of times context matters, right? A single amino acid change may not be the answer. You might need to include many different amino acid changes, but now you can see a combinatorial explosion starting to happen, right? So you have a semi-rational approach, but you need a sledgehammer at the back end to sort out everything you're doing. The other approach we have, I didn't talk about this at all today, but design of experiments, right? How can we look at all the variables that are in the experiment and then define the minimum set of experiments that allows to access those variables? I mean, at the end of the day, biology is, you know, no matter how good the tools are, biology remains as unpredictable as it ever was. And so, this is where I think it's a mix of sledgehammer and, a finely tuned scalpel that I would say that allows you to get the final solution.
Okay, thanks. I was wondering earlier, I'd like to ask Paul actually to put his microphone on. Paul, I saw in one of your slides earlier, you were mentioning the fact that in London you've been working on cell-free approaches. Could you say a little bit more about that as well? That's quite an interesting development.
There's probably several years ago, there's a bunch of us adopted cell-free lysates. Now, cell-free lysates transcription translation systems have been around since the year dot. And they're very much used for protein production methods, or trying to get a protein that can't be expressed in E. coli expressed or whatever. But they've been energized through synthetic biology, and for the last sort of 10 years, a bunch of us have been applying them in different ways. So biosensors is another opportunity, so cell-free biosensors, and there's a lot of work done on that. I've been using them for that, but also for prototyping parts, so for non-model organisms. So for example, the Bacillus megatherium, which is an interesting and potentially industrial strain, has got very few regulatory elements that are characterized. And so it's quite a difficult organism to transform as well. And so by building libraries of BMEG parts and then screening them using a BMEG cell-free system, you can get data, quite interesting data quite quickly, to allow you to sort of like start thinking about designing libraries of regulatory elements for those kind of organisms. I've also been using it for natural product discovery and production. So quite a lot of the actinomycete strains like Streptomyces have billions of enzymes that are not expressed, or these cryptic clusters that are not expressed. So we've been building Streptomyces cell-free systems, and we've been expressing these enzymes, and we've been looking to see what products they make and things. So there's a discovery side to it. And then finally, there are people over in the States, particularly Mike Jewett's lab, who feel that cell-free systems, and this is also shown by Sutro Pharma, who used E. coli cell-free to make monoclonal antibodies, but could be actually a production method and an economically viable production method. And there's a lot of very nice work he's done, and some techno-economic analysis recently done on cell-free systems versus fermentation. And, it's not, it's an interesting area, and I would keep an eye on it. And the beauty of cell-free systems, of course, is that, they can be distributed. So you can do distributed manufacturing, you can freeze dry cell-free extracts. And so the energy source is an issue, but you don't have to have clean, big stainless steel vats and things like this. So I think there's a lot of people are very interested in cell-free systems for both for manufacturing, but certainly in the prototyping and product discovery and chemistry, no doubt they're really very powerful.
Okay, thanks. Still on new developments, new approaches, new thinking in the area. There's a question that's been put up. It's all about going from batch mode type logic to continuous mode. Maybe Katja, would you like to take up that subject? So the question is that bioprocesses seem mainly to be developed following a batch logic. And how do you see the introduction of more continuous bioproduction systems in the future?
So actually, we have really an IBISBA and TNA project where this is really an issue to move a batch fermentation to a continuous fermentation process. So it's not often the question. So yeah, you are right. Often there is a batch logic, or at least fed batch logic. But I think also we have in IBISBA we have Vito included, which also have the know-how to have in situ recovery systems, or to develop in situ recovering of the products and so. And this allows to run fermentation also in continuous mode, to continuously remove the product. So depending on the strain, the process, or the product, this could be a good way to optimize processes and also to make it feasible for industrial scale.
Okay, thanks. And maybe before we move on to other subjects, I'd just like to wrap up the subject about the downstream processing that we discussed earlier. It seems to me, but maybe I'm wrong, we have very, very strong developments in, for instance, we've seen this afternoon in the biological sciences with new concepts like the Biofoundry concept. And there was a very interesting point made by Sunil, where he said, you know, in a way, we're just moving bottlenecks along the line. And it seems to me that downstream processing is now becoming a bottleneck, because there's a lot less, or it seems to me as somebody from looking in from outside, there seems to be a lot less innovation and dynamics in the downstream processing area than there is in the upstream strain development area. Do you feel that's true? Or, I mean, we seem to be still very traditional. I don't see very many new technologies for downstream processing arriving. Do you think we need more innovation in that area as well, and maybe co-innovation with the upstream development?
Yes, I think so, that we have to have this innovation in this field, of course. You're right. Normally, so it's also the same at Fraunhofer CBP. We have state-of-the-art equipment for DSP. Could be separation, could be crystallization or membrane filtration. And there's only the innovation if you want to change a membrane, for example, to make it better or more feasible for your product, or to connect the separate parts of this DSP together and combine it for a more optimal process. But I think there should be also more innovative research on DSP. So to really include maybe membrane filtration directly to the bioreactor, for example.
Okay, thanks, Katja. So maybe I'd like to move on, because there's been a few questions throughout the afternoon about intellectual property. We've also talked about the increasing need and use of advanced data technology and artificial intelligence. So maybe I'd like to keep some time for that. The first thing, maybe we'll talk about the computing resources part. I mean, several speakers have talked about that and the need for more and more computing power. I was wondering, how are we dealing with that at the moment? And for instance, in Ameris, Sunil, is all of your developments mainly in-house, or are you using whatever is popping up around the world? Are you using open source software? How are you dealing with that?
Yeah, I mean, it's a combination of everything you said. I think, again, when we started building our pipeline, we didn't see a lot of tools out there that we could easily bring into our facility. So we started building our own. Now, when you start building your own, then when someone else comes up with their own solution, it's a challenge to integrate that into your own pipeline. That being said, I think today there are quite a few, for example, machine learning algorithms, right? I mean, there are plenty of companies that have very good algorithms that you can port over and then fit into your scheme. So we do a lot of that. Cloud computing is something that we are definitely relying on a lot. That is actually quite a big difference from how things were operating 10 years back. I think there are definitely companies that we're looking at now where we believe, hey, maybe we looked at this 10 years back, it wasn't mature enough, but now it seems to be something that we can definitely factor in and use within our pipeline itself. So I think it's a mixture of everything. We did develop it on our own, but we are definitely, we keep looking for options out there. Open source is a great point. I mean, GSL, our genotype specification language, it is open source. We published on it. It's available. Autodesk has also released it. So that's an example of how we also try and get into the open source community with some of our techniques.
Okay, thanks. Paul, it seems to me that what you said about the Global Biofoundry Alliance, one of the key areas where this alliance can really make a difference is maybe accelerating the arrival of new software and new computing resources. Yeah,
thanks. Yeah, I think, Michael, that's a very good question. And one of the software working groups working very hard to deliver that. I think there's a real opportunity for large open source developments that can be shared widely around the world. And the other thing about software is that by having a multiple foundry environment, you can test things very, across different foundries. So in some ways it's a really great test bed for different software algorithms, different workflows and different processes. And certainly that is one of the aims of the software group, to try and build those tools and accelerate the whole uptake of the idea of the BioKat design, the measurement issues, and some of the LIMS systems that people are using. I mean, academia, LIMS is a sort of, it doesn't exist really, but obviously in industry it does, but in Biofoundries it's essential. And so, you know, there's some really great products out there that you can try and collaborate with, but also people are building things themselves. So it's a balance between, you know, internal building and software developments, and also trying to take other freely available software and integrate it into various pipelines. But yes, you're absolutely right. Software is a great development for the Biofoundry community.
Okay, thanks. Olivier, Toulouse White Biotech must be looking carefully at these sort of opportunities of how to introduce more and more computing resources into your daily business. What's your thinking on that? What are you going to be targeting in the future in terms of beefing up your computer resources?
Well, I guess a couple of things. I think what we, from my past experience in product development, what I have seen are projects that were kicked off based on assumptions on, you know, markets, on product performance, and that were run, and these assumptions were not revisited based on the performance that we got at the lab or the pilot scale. And I think one of the key aspects on the data is how we can, in a systematic manner, take the experimental data and revisit whether or not there is a business case for a given project. And so this is one of the needs we have identified with our partners. And I would say similarly, we have the same needs from life cycle analysis or, you know, sustainability analysis of our projects. So this is for us one of the strategic orientation we want to take.
Okay. Earlier, we talked about public biofoundries. So Paul was sort of saying that the Global Biofoundry Alliance is an alliance of public biofoundries, pre-competitive research. I was wondering, and Sunil earlier mentioned about really the next question for everybody is, how should we go forward? Should it be each for his own, or should we be working in sort of hubs and networks? I mean, how do you see that, Olivier? I mean, what sort of models can you imagine in collaborative models for the future?
Well, to tackle that question, I think I would first go back to the investment, the capex required for these biofoundries. You know, Paul mentioned earlier Ameris, Ginkgo, Zymergen. I think there is something in common with all these companies, is that they had to invest hundreds of millions of dollars in the facility. And so when you think about it, when you're a private company, you have to think about the IRR. Now, looking at that from a public biofoundry perspective, I guess there are two questions. One is who shares the risk with you, and the second one is how do you have an impact? And so on the risk sharing side, you know, even if the government, public government are paying for such investment, the size of the investment is so huge that we need to make sure that industry participate. I think industry really needs to put its skin in the game in this respect. And so I think we really have to go towards a public-private partnership in this respect. Okay. When it comes to the impact as well, here, when you invest, when governments invest such amount of money, they want to make sure that there will be a positive impact on the society. And here, we are thinking two words. The academic word first, Badik wants to be able to use Biofoundry. They want to generate results and to be able then to leverage and improve those results. So we need to make sure that on on the intellectual property side, on the IP side, that academics basically own the IP and can use it. At the same time, the industry players here who are going to use the Biofoundry, they want to make sure they get the product on the market at the end of the day, and they want to make sure that this will be a competitive advantage as opposed to others. And so we need also to find to find for them a mechanism to be able to if not own the IP, actually at least get the right to use the IP however they see fit in their own business. And so I think this is this kind of public-private partnership that that the Biofoundry could favor. As we've done that within TWB with some success so far, trying to really easing how the IP can be dealt with based on the partner and based on however they want to use it.
Okay, thanks. Maybe Paul, can you briefly tell us what's the business model for your Biofoundry in London?
Yes, it's a mixed model. It's doing projects with companies, collaborative projects for funding. And so a company would come along, ask to maybe develop a workflow or look at some protocol that they just want to see. They might even just want to understand what the capability of a Biofoundry is. That would be a larger company, and we would just charge them, we'd do a collaborative project with them, but they would own all the IP from that project. We don't take any of that. And then in academia, it would just be the standard model of an academic collaboration project, which would be grant funded. So we have a private, public funding model. We found that working with industry where IP is not an issue, i.e. we don't take any claims over anything, is very easy, much easier for us and much easier for industry. And we get that's one of our USPs, actually. People really like that. The other point to make is that not everyone wants to take a product to market. Some people just want to investigate a bit of technology for one of their process development R&D pipelines. Someone might want to, just a startup company might just want to prove a bit of their technology so that they can get some investment in. So there are, not everyone goes from gene to, that 2,000 liter fermentation product. And I think that's the beauty of Biofoundries, is that they're incredibly adaptable and flexible and can work on many different aspects of biotechnology, not just industrial biotechnology, but also other types of biotechnology applications as well. That works for us, and actually we have a working group in the GBA looking across the world at the different public funded business models. Because they're expensive. Obviously, Olivier's right. The capex is expensive. If you're in the public sector, it's very hard to fund those things. So, but that'll be a very interesting piece of work, which is ongoing.
Okay, thanks. And maybe bringing Sunil back into this discussion, because you mentioned this idea of maybe the future is working in wider networks, in hubs, I think was the word you used. How do you see that working in terms of intellectual property and these sticky issues?
Yeah, I mean, and Paul framed quite well, and Olivier talked about this too. I think companies at the end of the day, what they're worried about, or labs, what they're going to be worried about is the IP on the final product. How you get there? Okay, I think people are going to be flexible around it, and so I don't think that's a concern. For a lot of companies, it's not just IP. There are also trade secrets. So sometimes the trade secret is more valuable than the IP itself, and so I think this is where a public-private or just a plain public Biofoundry that caters to different requirements from its different partners and customers is very important, right? Because the company is going to solve for its own problems. So, I talked about quantity and I talked about quality. I never talked about complexity, right? So, Biofoundry like Amyris is, we will focus on the one problem or the few problems, and we'll try to keep, focused on our problems. But who's solving for the complexity of all the different requirements from everyone else out there, right? There are plenty of other companies, plenty of other startups, plenty of other academic labs. Each lab has its own requirements. Solving for all that complexity is not easy. So, in addition to IP and trade secrets, I think the public Biofoundries also serve fill a very important gap, which is solving for complexity of everything else that's needed out there.
Okay, thanks. Vitor, maybe there was a question earlier about how IBISBA is dealing with IP today, and I tried to reply in the chat to that question. But not talking about today, but tomorrow, how would you? What's your vision? You know, as a member of this network, what would your vision be for dealing with IPR in the future within the IBISBA network when we're working with clients on multi-services?
Well, I mean, for the client, I would see this as being for the client one entry point that would, so that the client would not have to deal with, you know, all the 30 or 50 members of it. So that would be a simple way of dealing with IP that would be tailored. That will be a tailor for customers, but it should be kept as simple as possible.
Okay. Okay. So what I mean, maybe just to sort of wrap up, I mean, what I can see from the discussion we have today is that probably the future is going to be a very interactive future around this this field of biofoundries. We've just heard that, you know, maybe the way forward is sort of greater collaboration and even synergy between public and private efforts. Maybe Nick, as a last word and to wrap up on that point, how did it work out in Singapore in that respect, since they have lots of money and they don't have to worry about these things? Put your microphone on, Nick, please.
Yeah, this is, well, Singapore has a lot of money, but you still have to work hard to unblock it. It's just that once you've convinced the ministry, then it makes it a little bit easier to put it into place. But yeah, there is a very business-orientated approach to research over there, which is closer in many ways to the industrial model that Sunil is talking about. It has to add up to good sense. There is probably a little bit too much emphasis on IP. There's a very, shall we say, strict on IP negotiations, which I think can sometimes be a deal breaker. That there's room to move on that, I think. But basically, yeah, Singapore is beginning to work like a village. It is a small country. There are lots of very, very good universities, and there is a web sort of network being installed to share the costs of this expensive apparatus and make it available as much as possible to the other teams who might have occasional requirements to use it. It's I think this comes back to the web system. Do you need a hub to do this? Obviously, not every lab who does metabolic engineering can afford to invest in a biofoundry. And I think this is clearly where we can share the facilities, make them more available. I think that this is certainly part of the Singapore attitude to this. It is, yeah, obviously you do that with academic partners at a different conditions than you do with an industrial partner, but it is the idea that if you make that type of investment, even if a country is rich, you want to make money out of it. You want to make it to pay, and you don't want to duplicate these investments. It's so yeah, there is a strategy, but it's possible in a very small country. It is easier to do than in your full European level type logic.
Okay, maybe a last word for Olivier, and then we'll wrap up this panel discussion.
Yes, Mike, thanks. Well, you know, Sunil mentioned something that I think very important. He mentioned, and you know, I lived through that the company, they have to solve for their own problem, their own product development problem, and there is the whole world of complexity out there. And I'd like to take an analogy on how private and public biofoundries could work. When I was in the tire industry, I was in the polymer innovation world, and we were doing real state-of-the-art innovation in polymers because we had some polymer plants, but only 2 of those. And what we were doing was new polymers coming there where we had a lot of value we were putting in our plants, and those were actually replacing former innovation that we would outsource. And I am wondering, you know, if in a way private biofoundries could at some point outsource some of their innovation they have put together, but they don't really have value of running them right now, to outsource that, so that the public biofoundries can take up on those, can kind of standardize and propose that to the whole community, while the private Biofoundries continue to work on what is important for them in terms of solving issues that are at the forefront of science usually.
Okay, thanks, Olivier. You've just opened like a new panel discussion for our next meeting, but we won't have time to discuss that this afternoon. So as the sort of chair of the panel, I'd like to wrap up now and thank the different people who intervened. It's been an interesting afternoon, and I'll leave the last word to our chair for the afternoon, who was Nick until I took his place. So Nick, the last words from you.
Yeah, the Booby Prize, trying to wrap up such a diverse and interesting session. First of all, let me thank everyone who's contributed, either actively amongst the panel, the speakers, but also some of the interaction between the participants, who've been asking some very good questions, I think. I think what we've learned a lot today. I think we have to bear in mind that biofoundries are enabling technologies which were designed to meet a specific tasks, and those tasks will continue to evolve. We've had some questions on accelerated evolution, if you can actually increase the diversity of evolutionary trajectories, of course, you have more chance of finding the right strain. And these have been used quite a lot at the moment, using biofoundry type technologies. We're also using it more and more, Sunil mentioned it, not to use the sledgehammer approach in metabolic engineering used to be just overexpress the gene and ultimately poison the cell by protein burden problems. We're seeing that we can now explore a much wider synthetic biodiversity by using these platforms to design different enzymes, which we can then integrate back into our metabolic engineering. So we're opening up a sort of an artist's paint set, which now gives us unbelievable facilities. I'm still a little bit waiting to see how we're going to inverse some of the logic. I would like to think that in a sort of more holistic vision of industrial biotech, but it equally applies to fundamental knowledge drive to actually reverse engineer the process and work out how can we build into our strain engineering concepts which will make the scaling on the downstream much easier. It's one of the things I learned when I worked with the pharmacy, 90% of the cost is the downstream. So if you don't have to produce necessarily more of the compound, but you want to produce it so that it's easier to purify. And this is a slightly different concept to what we're doing in our strain engineering, but the same platform technology can apply to that. Huh? So I think this is, as we look and ask the right questions, the Biofoundry technology will be able to provide the solutions to us. And I think that's great. The other take-home message I think I got quite clearly coming across from some of the exchanges is the CapEx investment in these biofoundries. I just signed the check a while back for the one we built in A-Star in Singapore. Not every lab can do this, and we really do have to work out how can we make these facilities accessible so we can draw the innovation network as wide as possible. And we don't really want sort of game-changing ideas to not come through the pipeline because people are not getting access to these facilities. So there's clearly a requirement to democratize the access and to have skilled workers. You know, even if everyone could buy a biofoundry, the level of skill you have to put together to make it work efficiently is an additional manpower cost. If we can actually group that around a small number, debatable number of hubs, which regroup the necessary expertise and the facilities, then I think we have a big effect on driving both knowledge and applications forward. So that I think we have to work on. There will be IP issues, that's come across a few times. In my experience, IP issues, if we go into this with the right attitude, can usually be resolved. It's very seldom a major stumbling block as long as people's ideas are reasonable. So I think that we have a potential. We've got to build it now into the overall pipeline. I like Sunil's idea that it's not just a biofoundry. The biofoundry is one piece of the puzzle. And if you want to drive this through to the end, the puzzle has got to be put together in a way that makes it coherent as an overall pipeline. And I think that's going to be where the challenge is. To conclude, perhaps IBISBA is one potential hub which reunites together many of the pieces. We're probably going to find we're still missing pieces as we go forward, but that the open network type logic will allow us to bring these people into build this. So I think, yeah, the future is there. I would say for those who are out in the audience who would like to try and to experiment this, I will remind them that we have regular calls within IBISBA for interesting sort of, not really pre-competitive, but early stage projects to try and get feasibility studies. Yeah, try your chance, put in the grant request. It's a very short document to fill in. And yeah, this week we can sort of open this up progressively. Once you've got feasibility studies, you move to the next level of grant and build bigger projects. But I think the facilities are there at the moment. We now have to learn how to use them. We probably also have to temper down the expectations that these foundries work when they're well run. If you just plug it in and try to do anything, nonsense in becomes nonsense out. And I think this is where we probably have to reinforce the hub so we can give a good advice on how best and what is feasible in the Biofoundry situation, and not waste people's money doing experiments which have virtually no chance of success. So I think that's the word of caution at the end, but basically, as we've heard today, there is unique possibilities to explore ground which even a few years ago we couldn't dream about exploring. So I think that is good. I think this is great for industrial biotechnology. And now, just as I think it's Nike who say, just do it. We've now got to sort of put it into action and drive it through, show that this will be a game changer. I think we all on the panel believe it. Now I think we have to show it with some concrete examples, and they're there in the literature, but the more there are, the better. So I think perhaps just to finish off, we just we'll thank the BioKat people as well. I see they've come back into the picture for this possibility to run this workshop. I've been keeping an idea on the participants. We've been regularly above the 100 participants in a virtual workshop. That is good. Yeah, no doubt this has been a turning audience. It's falling off as it was predicted it might towards the end, but that's inevitable. I think hopefully we will have stimulated interest in people who may not have understood fully what the capacity of the Biofoundry system is, and hopefully we'll have got some new potential collaborators coming into the system to contact any of the speakers who've been talking about this over the time. Huh? So thanks for everyone for taking part in this workshop. And I'll hand it back perhaps to the BioKet organizers if they want to say a quick word to close the workshop. Huh?
Okay, thank you, Nick. Yes, indeed, we would like to thank IBISBA and all the partners and speakers today, particularly Michael for having entrusted us for this webinar. Nick for the very nice moderation of this webinar. A wonderful job to manage this webinar. Now, indeed, we come to the end of our trilogy. We hope that you enjoy the program. We'd like to thank again all the partners for those webinars, in particular Indrae and the Institute Tribeca for the webinar on the phenolic acid yesterday, ValueMag and all its consortium for the webinar on Tuesday, on microalgae, and obviously IBISBA for today's webinar. Last remember for our next event, BIOKET Digital will be back in September with a new H2020 project, the project enabling BPP, a project encouraging the creation of efficient and structured biomass supply chain for the production of bio-based products. Should you like to promote a key enabling technology you're developing, and should you like us to host, promote, and handle your webinar or workshop, please don't hesitate to contact us. We are ready to help you to promote your technology. We plan to have a monthly webinar, and we are still open for October, November, and December. And obviously, we were happy to be online this week and to be able to deliver part of what we were planning to deliver last March. Thank you very much for your understanding. For BioKet on-site. And in the meantime, I would like you to stay healthy and pay attention to yourself and your loved ones. Thank you very much, and have a nice and wonderful afternoon, and keep safe, and we see each other hopefully in March, and maybe earlier for those who collaborate more often. Thank you very much. Have a nice evening. Bye-bye.
Thanks, everyone. Bye.